It sounded like Christina was lecturing Mark, so yeah, that was kind of funny.
Well, you know.
All right. Should I just get started, or Mark, you have anything you want to say first?
Nope, just start sharing your screen, and don't forget to introduce yourself as the lecturer opposed to the dean.
Yeah. All right. Let's see, which one is it going to pick here? Okay, so I think this is my first one. All right, so I'm Christina Cohen. I'm at Caltech. It says right here. I'm one of the deans. And if you can guess, I study energetic particles, specifically solar energetic particles. And this was a view that I talked about yesterday, where you're actually seeing energetic particles hit the detector of LASCO and cause all this, what we call snow. So this particular, I have both the lectures this morning, and I will warn you that this lecture is overly packed. I'm going to try and go through it. I will apologize. It's probably going to be a bit rushed. But if you want me to go back to anything, maybe we can talk about it during the office hours. And if I go over, I think the next one's a little shorter, so I might borrow some time from that one. So we'll see how this goes. Okay, so energetic particles. Let me get my laser pointer here. Okay, so there's lots of different types of energetic particles in the heliosphere. Many of you probably know most of them. There's galactic cosmic rays, which are coming out into our heliosphere from the interstellar medium. There's anomalous cosmic rays, which we think are accelerated somewhere probably around the termination shock. There's a lot of discussion about this. There are radiation belt particles around the planets. Mostly we've studied those around Earth and Jupiter. And then of course there's solar energetic particles, which is the thing I'm going to ignore everything else and basically just talk to you about solar energetic particles. And that alone will be more than enough for this lecture. Okay, so let's start with what they are. Well, they're basically what we say they are. They're solar, meaning they assume to originate from the sun. They're energetic. What that means is a little different for different people, but historically it's been above a few hundred keV per nucleon. And of course they're particles. This is ions. Generally, they're not quite fully stripped. Certainly protons are. Helium is generally fully stripped. The heavier ions, some like carbon, generally, iron less so, and then electrons as well. And they've basically seen, when we say an SEP event, they're seen as increases in the counting rates or in the intensities, generally of electrons or ions. And again, usually energies above 100 keV per nucleon or so. So now it won't move. That's really weird. Okay, sorry. So let me just do a really quick brief history of SEPs. Basically, they were sort of the first detected on the ground in connection with a solar flare. So we've been observing cosmic rays on the ground with muon telescopes and neutron monitors, which I'll talk about a little bit for a while. And Forbush in 1946 was the first to say, hey, maybe this is actually connected to the sun. And then they did this study where they saw this really nice increase in a neutron monitor detector that went up and came down, and they actually timed it. This timing of when it went up was nicely correlated with an actual gamma ray flare that they observed. And this happened in 1956. Remember, this is before the space age. And so this was actually pretty impressive that they were able to connect these things. Of course, since then, it's much better to observe these things in space because we can see them directly. We can measure their intensity, their energy spectra, and their composition. And this allows us to do what all good scientists like to do, which is classify them into all kinds of different groups. So at the same time people were doing this with SEPs, flares were also being observed in a bunch of different ways and being categorized by their size, their duration, their emission, a lot of the stuff you heard Enrico talk about yesterday. Also radio emission was being detected and categorized. And basically they lumped those two together and they combined two classes of flares, basically. You'll find that in our area, at least, a lot of times we like to have two classes. I don't know why. Sometimes we can't. We can count all the way to 3 or 5, but 2 seems to be a nice number. So there are sort of two groups of flares. There was one that was called impulsive, which meant it went up really fast and it came down pretty fast. It was pretty short, minutes. and gradual ones that went up and took a much longer time to come down. When I say much longer, we're talking maybe an hour or something, so not like super long. And then basically these were combined to get, together with the SEP events and their characterizations to create two classes of SEPs. And basically you can think of them as this kind of matrix. We borrowed the terminology from the flare people and called these SEPs impulsive and gradual. And the flare characteristics were just what I said. They were either short or longer. The impulsive ones are a very compact source. The gradual ones were a larger source. They had certain types of radio characteristics, which I'm not going to touch on this at all. And then the important thing was the SEPs had very distinct particle characteristics. In particular, the impulsive events were helium-3 rich. They had a lot of electrons. They had a lot of heavy ions. They were small. And then the gradual events were much larger. They were sort of like the solar wind in composition. And you could kind of see them when I say over wide longitudes. Remember at the time we were only observing from one point, so we could see them wherever sort of the source region was on the sun. So, so this is sort of like what you would sort of a canonical look of what they would look like. This is a gradual event. This is different energies of protons, and there's electrons in here somewhere, the asterisks. And you can see that they go up pretty quickly and they last for days. And an impulsive event basically goes up and comes down fairly quickly. So it's a much smaller event. And you'll see that the electrons here are much higher than they are in here. These have a lot of protons, particularly at the 1 MeV level. And so it was really nice to have these two classes. It did form a distinct paradigm shift in the 1980s when once we started observing CMEs with Skylab and such, to suddenly say, oh, well, we had these CME events as well as the flare events. And suddenly now we have sort of two acceleration mechanisms, and those began to be related to the two SEP characteristics. And so we had this old picture where flares were the only things that were accelerating SEPs, and flares could happen all around the sun, and they accelerated particles sort of in every direction. If you were at the right place, you saw them. The new picture now was that flares happened still, and they accelerated particles, but they only accelerated over a narrow range, and only if you happen to be at the right place would you see them, and what you would see would be an impulsive SEP event. And in contrast, we had CMEs that would go out, drive shocks, which would be a very broad longitude. They would accelerate particles all along that shock front, and so they could populate a much wider region of longitude with SEPs. And so you didn't have to be at the right place at the right time to see it. And this would give you a much bigger event because the shock could accelerate particles along the way, whereas the flares just sort of threw everything out in one shot. I'm not going to talk about this. This is a whole nother talk, but let me just tell you that, so the idea behind this that was really nice was the thought that if you measure the characteristics of the SEP events, that automatically told you whether you were looking at flare acceleration or shock acceleration, and the two didn't mix. You just had one or the other. Once ACE got launched in 1997, it saw a bunch of events that basically questioned this whole picture. And basically the upshot was now people believe that they're not quite mutually exclusive in terms of the SEP characteristics. They're still two separate acceleration mechanisms. Flares is basically reconnection close to the sun, and CMEs is like shocks, as I mentioned before, and we'll talk about that a little tiny bit. But you can't determine which one is operating just by looking at the SEP characteristics. So that kind of messed everything up, but it's probably a truer picture of what's going on. Okay, so why do we care about SEPs? Well, of course, you guys have heard some stuff about space weather. I don't have time to go into it. I gave an entire 50-minute lecture last year on space weather. I think that's recorded, so if you want to go back and look at that, you can. Basically, SEPs is one part of space weather. They cause concerns for satellites. As you see, the snow on LASCO means that, it has a hard time seeing a CME if it's covered in, these energetic particles causing streaks in the detectors. It can also cause event upsets and cause instruments and satellites to turn off and go into weird modes and cause all kinds of problems. And of course, those energetic particles can get into the Earth's atmosphere and cause lots of other problems. They also cause aurora, which are pretty nice, but lots of other problems. There's also space weather actually out at other planets. It's not just Earth that's special. We can see space weather events at spacecraft out by Mars. Certainly CMEs get out there. And so that's something that people are starting to look at, especially if we send people to Mars, then you have to worry about the space weather and the particles hitting the astronauts on the way out, and that can cause all kinds of health problems and such. Okay, SEPs are also interesting just for science. The particle acceleration that happens for SEPs happens all over the universe. In particular, shocks, we see them at CMEs, as I just mentioned, for solar energetic particles. We also see the bow shock in front of our heliosphere, so the heliospheric shock. There's also one, of course, in front of the Earth. These all accelerate particles. We also see them in supernova and astrospheres and things like that. So this same acceleration process under different conditions is happening all over the universe. So understanding it here where we can look at it really closely is really important. And of course, the other acceleration mechanism, reconnection, sorry. Yes, it happens at the sun with these flares. You can see this little interesting thing here, which is reconnection. It also happens at the Earth's magnetosphere, which is part of what happens during geomagnetic storms. And of course, it causes the aurora, also at Jupiter, as well as happening in the tail, which is leading to the aurora at Earth. So there's lots of places reconnection is going on that we want to study as well. So how do we study them? Well, next lecture is going to tell you all about the actual detectors and how they're built and what methodologies go behind them. So I'm not going to talk about that here. Locations, generally, at first we were just launching stuff really close to Earth, and there's still a lot of spacecraft that are basically just orbiting Earth and looking at SEPs. A common place that we've sent a bunch of things is L1. It's the first Lagrangian point. It's basically a balance point between forces from the sun and forces from Earth, gravity and such. It turns out it's actually a little easier to orbit that than just sit there. So this obviously is not to scale, but it's about 1% of the way between the Earth and the sun. So it's 1 million miles or so closer to Earth, closer to the sun than the Earth is, but this distance is almost 100 million miles. So we're talking about big distances here. Right now, there's at least 4 spacecraft there, ACE, Discover, Wind, and SOHO. They're actually, unlike this picture, on slightly different orbits. So they're, and there's actually a lot of space there. So they're not likely to run into each other, but they're all sort of sitting here. We all talk about them being at L1. There is some plans to send instruments out to L2, but I won't really talk about that at all. So an interesting thing is, with all these measurements, whether they're at Earth or L1, you're getting sort of one view of the sun. You just have one spacecraft, stuff is washing over you. You're not really getting a, varied view. And excuse me, in 2006, we launched the stereo spacecraft, which is like very innovative in a lot of ways. It was 2 identical spacecrafts, so they had the same payloads. And basically one was launched in an orbit such that it moved a little bit faster than Earth, and the other one moved a little bit slower than Earth. They all sort of, of course, orbit the sun, but if you look at a reference frame where Earth is fixed, basically these 2 spacecraft kind of drift around the sun, and they actually cross behind the sun, and now we're coming back. Unfortunately, we lost stereo B, so they're called stereo A and stereo B, which I know is very clever, but it's better than 1 or 2. And we lost stereo B around 2014, just just before it crossed behind the sun. Stereo A has actually come all the way around and is actually very close to Earth, and will pass Earth in the next couple of years, and then we'll go back around. Hopefully it'll keep working. So that gave us a really new view where you could measure now things from multiple vantage points, not just from the 2 stereos, but you could also combine them with the L1 measurements and now get sort of 3-dimensional stuff, which was actually pretty cool. Once a long time ago, we actually had Helios, which was 2 spacecraft, and they were in these crazy orbits. They weren't synced up, so they would go in closer to the sun and then come out. And so you got all these kind of gyrating different configurations. And so there was some really interesting physics that was done there that I'm not really going to touch on. They were, of course, a lot earlier, and so they were more limited in terms of their instrumentation. But now that we have some other spacecraft that are going close to the sun, which I'll mention at the very, very end, people are sort of resurrecting some of these data and making comparisons. Okay, so we've got all these assets, all these things moving around. So why is it really hard to kind of characterize and understand what's going on? You would think this would be, we got lots of measurements, shouldn't be that bad. Well, this is sort of a rough map of how things go. So you've seen these things, right? This is sunspots on the sun, and sometimes they erupt, as you can see in these nice movies, and sometimes that creates a flare, which we can see with the X-ray goes things, and sometimes that flare actually accelerates energetic particles, and people like me are very happy. But sometimes you get that flare and it doesn't accelerate any particles, at least ones that we see with whatever spacecraft we're looking at, and people like me are a little sad. Sometimes what happens is you get that flare and that's big enough that it drives a coronal mass ejection, which drives a shock, which you can see with the coronagraphs, and that creates an SAP event. And again, somebody like me is very happy, but sometimes that shock is going too slow and it actually doesn't create an SAP event. And so generally what you can see is it's very complicated because all these processes are going on and sometimes they happen, sometimes they don't, and they all happen at the same time. So the other reason why it's really hard is it seems like everything varies with everything. So I'm going to show you a few things. These are SEP events. This is intensity. This happens to be oxygen as a function of time. We saw that different energies here, and you can see a whole bunch of events. There's at least 5 different events here. The flares are marked here. This was a very, very active time period where we had 7, 8 different X-ray flares above the X class level, which is sort of the highest level that we measure. And then these solid lines are shocks that we saw passing the spacecraft. And you can see these events change in terms of how big they are, in terms of where they peak, but also how long they last, how many particles are involved. Also, if we zoom in, now instead of looking at days, we're just looking at hours as they start, you can see that some events start and go up really, really fast. Some events take a much longer time to go up to high intensities. And so, you get a lot of variability in terms of the onset, in terms of how fast it is. So the other thing is if you integrate over those and you look at essentially the number of particles as a function of energy integrated over the whole event, we call that the fluence. Sometimes we convert it to actual density is what we've done here for protons, plot that in terms of energy, and you can see that the shape can be very different from event to event. And the reason why that's important is if you're only interested in particles, say you're an astronaut or something, and you're inside a fairly shielded area, you may only be worried about particles that are greater than 100 MeV. Well, if you get a smaller event that basically most of the particles are gone by then, you're not worried about it. But if you get an event like this one in January 2005 or February 1956, where there's a lot of particles above there, then you're really worried about that type of event. So again, they vary from event to event. This is a bigger survey. These were sort of outstanding events. This was sort of more like everything we've seen over 2 solar cycles that were above a certain size. And you can see even here, even within a solar cycle, the blue ones are generally different shape than the red ones are. And so, but there's order of magnitudes difference here. I mean, every one of these ticks is a factor of 10. So you can see this is several orders of magnitude different at the highest energies. Okay. So if you get a really, really big one, it can actually interact, enough protons can interact with the atmosphere of the Earth, and we can actually detect the neutrons or muons that come out of that shower. I'll talk about that a little bit more in the next lecture, but if we measure them with neutron monitors on the ground, those are called a ground level enhancement event or a GLE event. So you might hear that term. That generally means that you had a lot of really high energy particles. Doesn't happen a lot, but when it does, everybody gets either excited or concerned depending on which side of the fence you're on. The other thing that varies a lot is the composition. In these instruments, we can measure elements basically from protons, typically all the way up to iron, but sometimes we can measure even heavier things like zinc and copper and things with mass of hundreds and such. Typical is iron, but if we look at sort of, this is the number of silicon, basically the silicon fluence in the event, you can plot this, protons, whatever, this just happened to be the thing we looked at. But the thing that's interesting, if you plot the iron to oxygen ratio in that event, each one of these points is an event. This line is sort of the average of what we expect from sort of big SAP events. And you can see the scatter is enormous. For a given event, it can vary by an order of magnitude or more in either direction. It can be either what we call iron poor or iron rich. And it's sort of related to how big the event is. The bigger events tend to be in this range, but they can be all over the place. Okay. And then, as I mentioned before, what we used to call impulsive events, I will say that we're trying to get away from that impulsive gradual terminology, just because that implies that they're really separate, and they're really not, because you get flares and CMEs happening at the same time. You get acceleration happening at both. So now we sort of call them big events and helium-3 rich events. So the helium-3 rich events are usually associated with flare acceleration, the reconnection that's going on, and you basically see a lot of helium-3 compared to helium-4. Compared to what we see in the solar wind and stuff, the normal value is about 5 × 10⁻⁴. So you wouldn't really even be able to measure it and see it in this plot. So if you see anything, even a few %, that's considered a helium-3 rich event. What tends to go with these is also enhancements of iron and nickel and calcium argon, a little bit more enhancements of these guys in the middle, and then the helium and oxygen tend to be sort of normal. So these guys are, this kind of end of these points over here. But there's lots of variability even within the helium-3 rich events. As you can see, the helium 3 to 4 ratio here in these histograms varies. Okay. So we also have lots of assets, right? We have things that are looking at the sun. You're getting, I don't know why this guy isn't playing, but anyway, that's a CME. So we have flares, we have all this great detailed data. We have all these spacecraft. This is a fairly current view of what we call the Heliophysics System Observatory. These are all the spacecraft at NASA, and I think there's from ESA and JAXA that are on there that are looking at the sun. So you would think we are really looking at this stuff in great gory detail. So we should be able to sort all this stuff out and figure out exactly what's going on and be able to predict the characteristics of an SEP event, or at least understand why some are one way and some are another way. Well, the problem is this is a very deceiving figure. What's really happening here is it's not to scale, right? So if you split it up, it's basically all your assets are sitting somewhere over here, like where I am, near Los Angeles in California, and the sun is way over here in Hawaii. And basically I'm sitting here with my nice little, binoculars, trying to look at the sun and see what's going on. And then, and see if there's like a big wave or something, and then measuring the characteristics when that wave laps up on the beach in Los Angeles and trying to connect those two things. And the problem is that there's this big space in the middle, and we don't really know what's going on in there because we're not measuring anything in there. So you could say, okay, well, big deal. It's got to go a long ways. What could possibly happen in the middle? Well, there's actually a lot of stuff that happens in the gap. Some of it we understand, some of it we don't, and I'll go over that in a bit in the second half of this lecture a bit. But just to give you a couple of items, it's what we call transport effect. Basically, never mind the acceleration. Once you've accelerated the particles, now they've got to go through that big expanse. What happens to them? Well, one of the things they do is they lose energy. So if you inject a bunch of protons or particles, this is a simulation, of course, at the sun at like a very narrow range of energies, by the time it travels out to 1AU, these bundle of energies have distributed over a much larger range of energies because they're losing energies that are sort of proportional to how much they lose. So you kind of spread everything out. And of course, they're scattering. So they're not coming in a nice straight line. They're bouncing off the irregularities in the magnetic field and such on their way. And we can have interplanetary structures that are in between. Like you can have a CME that went off before the CME that accelerated your particles. And that's a big magnetic obstacle that the particles can't really pass through. Remember, these are charged particles, so they don't easily cross magnetic field lines. They hit a magnetic field line and they start gyrating and doing all kinds of fun stuff. So we see this. So these are marks of coronal mass ejections that were observed in the interplanetary medium in between this event. And you can see the event goes up, and then when the particle reaches the CME, you lose you lose a lot of the particles. So you can really change the structure in terms of which particles reach you based on what interplanetary structures between you and the particles. And then, of course, everything evolves, right? So as this CME propagates out towards Earth, all its properties change. So if it's accelerating particles, and the type of particles and characteristics of the particles depend on the properties of that shock, as that shock moves out, it's going to accelerate different kinds of particles, essentially, or to different energies as it moves out. And of course, what it moves into, the solar wind, you can see from these colors, it's not uniform all the way around. So if that CME goes into sort of a blue region, you're going to get one types of shock. If it goes into this sort of orangey red region, you're going to get different kind of shock properties, and that all affects the type of SEPs you get. And then, of course, what is accelerating? Generally, if you have a shock, it's going to accelerate the low energy stuff that's kind of in front of it. That may be some of the solar wind. It most likely is what we call the superthermal tail. What's in that superthermal tail can be all kinds of stuff. It can be stuff that's left over from previous ICPs. It can be solar wind stuff. It can be helium-3 rich. We don't actually know what is really going on in that region very well, and that's what's being accelerated. And it's not going to be uniform, so it's going to change all over the place. Okay, and then of course there's the problem that we don't even measure things sometimes. I don't know if this was mentioned yesterday, but of course, most of our measurements of, say, the magnetospheric, the magnetogram, the photospheric magnetic field, are taken just from the Earth's point of view, which means if you look at, this is sort of a Carrington longitude map where we've taken the sun and unwrapped it and made it flat, right? And these are all sunspots, and you say, oh, we've measured all the way around the sun. Well, in reality, we only measure sort of this section, and then we take another slice in time, and this section moves over here, and we measure a new section. And so we build up the map that way, which means that all the stuff over here is anywhere from several days to, a week or two old. And these things are not static. They change and with time, and that's going to affect what you're seeing. So if this stuff is around the backside of the sun, a new spot can come up, it could create a flare, and we won't know about it because we can't actually measure the backside of the sun. Okay, so really quickly, I'm going to go through these sort of what we know and what we don't know about these particular processes. Again, I apologize because this is the fire hose going really fast, but I'm going to get through as much as I can. Broad categories. We're talking about energization, so acceleration mechanisms. The two primary ones that I'm talking about are shock acceleration and reconnection. Transport, there's basically, going along the field and then going across the field, which I just said shouldn't really happen, but we're pretty sure it does under certain conditions. And then the conditions in which all these things happen, which, as I mentioned, is sort of the plasma you're going into, the structures that are there, and the characteristics of your seed population. What we know is basically, we know certain things from observations, so we know they happen, we can measure them. We can make correlations, so we know those things are related, and we can verify various theories and models. And so I put all that stuff in the category of what we know. What we don't know, of course, is stuff that we don't measure. Observations that we actually don't understand. I would classify that as we don't know something. And then some theorists may disagree with me, but I would say if you haven't actually tested a theory or a model, excuse me, then we don't actually know whether what you're modeling, what you have in your model is actually true. Okay, so let's go through each of these in order. So first is shock acceleration. What we know, this is what I showed you before. We see the shocks arrive, we see the particles increase at the shock, so we're seeing in action currently the acceleration of particles at a shock, and we can measure those things and look at the properties. So we understand the basic concept of diffusive shock acceleration and shock drift acceleration, and basically it kind of goes like this. You have a shock that comes out, and you have irregularities in the magnetic field on either side. And basically the particles kind of bounce back and forth across the shock. They're being scattered by the irregularities on either side. The thing is that, so every time they scatter, you can think of it as ping pong paddles, right? And so every time you scatter, you're going to, if they were just static, you wouldn't change energy. But if that ping pong paddle is moving, if it's moving against you forward, and you're going this way, you're going to gain energy. If it's moving sort of in the same way you are, backwards, you're going to lose energy. So this whole thing is moving. So you can think of it as the cartoon here. This side is moving, so you've got these ping pong paddles. So the particle comes here, it bounces off this irregularity, and because this thing is moving, it gains energy. This side is moving away from you, so it loses energy. The key thing is that these guys are moving faster than these guys, because remember, this is the fast material that is creating the shock. So overall, you gain more energy than you lose. And this is just a simulation where basically energy goes up, they're following a particle, the shock is here, it basically goes up here, it gets reflected, it gains a bunch of energy, it kind of travels back, it gets reflected here, it loses a little energy, and then it comes back and it gains more energy, and basically it goes on and on and on, but overall it's gaining energy. If the orientation of the shock is a little different, so that the magnetic field is sort of on either side of here is sort of parallel to that shock as opposed to, sorry, it's perpendicular to the shock normal instead of parallel to it, then you get what's called shock drift acceleration, where you get this reflection thing, but you also get these characteristics where basically the particle can drift along the shock. It's kind of confined right to the shock. And the magnetic field on one side is going to be stronger on one side than it is on the other side. And so that's going to affect the gyro radius of the particles. And so basically you can gain energy by the fact that your gyro radius is bigger on one side than it is on the other side. And you can kind of drift along the shock. There's also in some frame of reference, there's also an electric field, which will also accelerate the particles because it's ionized. And so you can gain a lot of energy pretty quickly. This is very efficient, but it's hard to keep a shock at that perpendicular orientation for very long. So this is actually much more common of what we see. But we understand all these processes and they kind of make sense with the observations. And we can actually do models and we can change the parameter of the shock. We can make them stronger. We can change their orientation. We can change the amount of turbulence on either side in our simulations and see how that affects the particles. And generally you get these profiles that look very similar to what we see in space. And we can actually try and model what we actually see in space at these energies. And excuse me, and they match pretty well, which says we pretty much understand what we're going on, what's going on and how these different parameters are affecting the particles that we see. And so the other thing that we see is that when we measure the spectra often have what we call the spectral break. So this is for one event. This is, protons through iron, and you can see these are fits through the spectra, and you can see that they're kind of a power law here, which is actually what the shock, diffusive shock acceleration predicts, is that you'll get a power law, which won't depend on the species of the ion. It actually be the same index, regardless of what element you're accelerating. But this drop off depends on basically the rigidity of the particle and how well the turbulence can confine that particle to the shock. Iron tends to have a higher rigidity at the same energy than protons, and so it will escape the shock region first, so you will drop off in terms of the number of particles that are accelerated by that shock. And so if we look at the energy at which these breakpoints happen and we plot them basically as the charge to mass ratio, which is related to the rigidity, then they seem to be pretty well correlated. And theory predicts that it will go like this, and sorry, the dashed line. The fit line is the solid line, and it's pretty close. And so, and it turns out that, the angle of that line can actually depend on the orientation of the shock and various parameters like the turbulence on either side. And so we actually can do a pretty good job of fitting these observations. So I feel like we kind of understand that kind of the spectra. And then of course, if you take a ratio of, say, iron to get the iron to oxygen ratio, and you take the ratio of iron and oxygen at a given energy, if iron's falling off faster than oxygen, then you get an energy dependent iron to oxygen ratio, which all kind of hold together and makes perfect sense. So we know a lot about these processes of shock acceleration. There's a few things we don't understand. One is that, as I said before, that the properties of the shock should accelerate things to a power law regardless of species. And we can measure that when the shock goes by, and we see the particles accelerated. We can measure both of those things and we can test this theory. And it turns out it doesn't always work. So this basically is the parameter. This is the compression ratio, and this tells you what your spectral index should be. This is the measured spectral index at that shock. It should follow along this line. Some do, but a lot of them don't. And then the other thing is that we know that if your CME is faster, it should accelerate more particles. Well, this is the CME speed, and this is basically the number of protons you have in any given event that were measured. And you can see, yeah, they follow a line, but there's a whole lot of scatter. This is orders of magnitude scatter here. So we're obviously missing some things. And some of it is that it depends on scales and the size and things like that. I already showed this plot where the composition varies. How you vary it by that many orders of magnitude and all these different events is not really completely understood. As I mentioned before, we don't really know what's going on about these particles really close to the sun. We don't know what the shock parameters are like at the sun. We can't measure it. We can see the CME, but we cannot measure the magnetic field in that CME and tell you what the shock parameters are in terms of, we have no idea what the turbulence is around it. We don't know what the orientation of the shock is. We actually don't even know quite where the particle acceleration starts and ends for any given energy. These are the GLE events that recently studied. Remember, these events that we've seen at the ground, they're the most energetic particle events. And we can use some analysis to kind of figure out what height the CME was at when those particles were first released, and look at it as a function of longitude of where that CME can, and it's all over the place. I mean, these are solar radii, so we know it's happening close to the sun, you know, about 2 solar radii, but all the way up to 6. And if you look at lower energy particles, excuse me, it's out farther. And so we don't understand, again, this variability, whether it has anything to do with longitude or not. We make these models and they can tell you parameters of the expanding CME, and you can look at, I know you can't read this, but basically this is sort of theta BN at a bunch of different times. That's all great and it all looks lovely, but it falls in my category of I can't verify any of that because I don't have any measurements right there. So I don't actually, you know, it looks great, but, and maybe I can correlate it with my SEP observations, but I don't know if that's actually the truth of what's going on. Okay. And then I mentioned before we had iron to oxygen ratios that were dependent with energy that fell. Sometimes they see them increase, which means oxygen and iron have different spectra, and sometimes they're power law spectras, but the spectral index is not the same, which leads you to this increase that we don't understand at all. There's some ideas that say, well, in this kind of event, basically you are, Nick, you've got a question?
Yeah, so there was just one, a couple of people in chat where somebody pinged me directly asking to slow down just a little bit. I know you're trying to get through a lot at the same time. We're trying to get through all and stuff. Yeah. So
yeah, I'll do my best.
Yeah, and maybe to help that, there's a question in chat: is SEPs are associated with CMEs or flares too?
Both.
Both. Okay.
Yep. Both. That's that. Yep. There's acceleration goes on at both, and the problem is that you can get energetic particles from both. They're different acceleration mechanisms, but they don't color their SEPs blue and green. So when they get to Earth or our spacecraft, we can't tell which was accelerated by which, because flares and CMEs generally happen together all the time. Occasionally you can see a flare that doesn't have a CME. And so then in those cases, we're pretty sure that all the SEPs are coming just from the flare. It's really hard to find the opposite. There are a few events where, like, you have a filament eruption and it creates a CME and there's no real strong flare. And we think most of the SEPs from that are probably shock accelerated, but most of the time it's a mix. And that's the hard part, is separating those things out.
And they don't come with name tags.
They don't come with name tags, unfortunately, no. Though we tend to like to name our SEP events. You know, we have like the Bastille Day event and the Easter event and things like that. But no, the particles aren't named. Okay, I will try and slow down. My guess is I'm not going to get through everything. But anyway, we'll see how it goes. So there's an idea of how to do this, basically, of getting this accelerated, and it has to do with the composition of the seed particle. And the idea is if you have an iron-rich seed population that you're accelerating more of that iron-rich part, then you're more likely to get this. This definitely falls in this category of unverified ideas. We haven't been able to show that this is actually true. It's a nice idea, but we're not sure it actually is explaining what's going on. Okay, reconnection acceleration. This is what's happening in flares. We know their event characteristics. I mentioned them before. You get helium-3, a lot of helium-3. You get a lot of heavy ions. You can actually get these really ultra heavy ions that are enhanced by a lot. So we know this kind of things happen. We know this is related to reconnection. We have some theory ideas. I'm not going to even remotely try to explain this, but basically it has reconnection at the flare. So this is sort of the erupting CME here. And then what creates the flare is you have a reconnection here, particles go down, they hit the Earth, the solar atmosphere, and create X-rays. And that's what we observe as the flare usually. So we know there's a lot of things going on in this reconnection region. We've simulated it. And we can accelerate particles in those simulations, and it seems to pretty much hold together. And so we think we sort of understand how that's going. We can also see radio emission, which is another sign of electron acceleration, and we can see that during an CME, and we can see it down in this reconnection region. These are actually observations here. This is a CME, and this is a microwave emission that's been observed. And we can also see the source region go off. We can see these little jets and things that we would expect to happen when you have this reconnection acceleration. So all that's really nice. And we think we understand it, but there's a lot of characteristics that we see that we don't understand. We see these events where if you look at the helium-3 here, it's really abundant compared to, in this case, it's higher than the helium-4, which is very strange. But you can see the shape of these spectra are different, right? And what energy things start to be accelerated at, we don't really know. As I mentioned, there's lots of variability from event to event. Sometimes they're bigger, sometimes they're small. Sometimes they have these characteristics. Sometimes everything's nice, straight power laws. The composition can vary. You know, if you pick an energy here to look at this composition, you get a helium-3 to 4 ratio that's greater than 1. Here it's going to be less than 1. Here it's going to be greater than 1 everywhere. So it varies from event to event. There's some idea that maybe there's a maximum amount of helium-3 that can be accelerated in these things just because of the sun characteristics, which I won't really go into. It seems to be kind of a ceiling here, which is not true for helium-4. We don't have any idea why that would be. These super heavy mass particles that we see an overabundance of, they seem to fall along this rigidity path, but we don't have any simulations that will really produce these kind of things. We can kind of do these guys, but this stuff, excuse me, we don't have any simulations that can actually recreate that. We also don't know exactly where all this stuff is happening. Reconnection can be happening here, it can be happening over here, where exactly the accelerated particles are happening, whether there's reconnection down on the flanks, we don't know. How they escape, you'll notice that this is a closed field region. So how they're escaping from this closed field region, we think they have to reconnect with some open field line that's on the side, but exactly how that works and when it happens, again, we sort of can do these hand waving things and draw these pretty cartoons, but we don't actually measure it. Okay, transport. I'm going to have to sort of skip over some of these things, but basically this is stuff that I talked about before. You know, we know the basics of E&M, right? The charged particle will gyrate around a magnetic field, and it will sort of travel along that magnetic field. So we know how that works, sort of what we call field line. And we know that there's cooling. That all makes sense with the data that we observe. We know that there's scattering. We can measure this sort of size of this helical path and the sort of cone it makes relative to the magnetic field is what we call the pitch angle. So if you get a really wide one that the particles aren't moving along the field very fast, they're doing a lot of gyration before they get, if it's really narrow, they're kind of just zipping along the magnetic field without making a lot of gyrations. And we can measure that. We can measure the pitch angle and we can see it change as time goes by. So we understand that that's a result of scattering. What we don't know is a lot. We don't actually know where that magnetic field is going. We have these models that'll tell you that this magnetic field line at Earth, or in this case where stereo B was, is connected to this active region. This is a model, and it tells us, and that makes sense because we saw an event. The flare went off here, and we saw an event at stereo B, and it makes sense because you're, in theory, magnetically connected. The problem is we also saw this event at L1 at ACE, which was, sorry about the different colors, but that was the black curve here. And we saw it at stereo A, which is the red curve here. And those guys aren't supposed to be connected to this thing at all. So we clearly don't quite understand all the magnetic connection to the sources.
5-minute warning.
Yeah, okay. All right. And we don't understand how all this varies. Across the field, we know it happens. We see observations from Ulysses that is way out of the ecliptic plane. You can see events that at the same time we saw something on the ecliptic plane. And we have some ideas of modeling that, you know, these field lines move around and the particles sort of, you know, scatter around and move around the field. And that all seems really great. But we don't understand how this actually works in practice. This was the event I just mentioned. You've got to scatter or move particles from this general region all the way over to here. We also saw an event like this where there's a big event. The CME went off the backside of the sun. All three spacecraft saw an increase in particles within 5 minutes of each other or 20 minutes of each other, which means you filled the entire heliosphere with particles within 20 minutes. And how you do that is not remotely clear. I'm going to skip this. And then the basic thing is, we don't know actually what's moving around, whether it's particles are actually tied to the field line, the field lines are doing something really wonky like this, or whether the field lines are relatively well behaved and it's the particles that are moving all over the place. We have no idea. Okay. There's transport and there's acceleration, and they're tied together because we're just measuring stuff at one point. And this is, sort of different ideas about how a single source could give you certain characteristics in the observed anisotropy of the particles. And we see all three of these cases, and we see events that don't even fall into these cases. So it's very complicated. The conditions I already mentioned, there can be stuff there that's in the way of the transport, but we can sort of see that. We know that they affect SEPs. We can see the solar conditions, as I mentioned. We can measure all this stuff. We can see the CMEs, so we kind of know what's in there, but we really don't know its characteristics. We can measure the particles, sometimes really close to where the CME went by. There's this thing called the streaming limit, which sort of limits how high an intensity you can get due to the waves that are, the turbulence that's created by the own particles. We kind of understand that and see it happen, but we don't know a lot of things. We don't know anything about where we're not measuring, as I mentioned before, when we don't have any data on the backside of the sun. We can't measure the shock properties near the sun. We don't know what the background solar wind is that the things are going into. We don't know how things vary, even on sort of medium scales. This was an event where we clearly saw the flare. Stereo A and stereo B were, in theory, really well connected, similarly connected. This is sort of the nominal foot points in the sun. They're right next to each other, but here's what they saw. And you can see that one spacecraft saw a very different pair of events than the other spacecraft, but they're like at the same distance and really, really close on these scales. And so how that happens, we have absolutely no idea. Seed population, superthermals. We know it's not the solar wind. And we know that there's lots of stuff that, it's basically being accelerated this region. We know that there's a lot of stuff that can contribute to that range. We don't measure that range really well. There's often a gap in here between the solar wind instruments and the SEP measurements. We're trying to fill that gap to kind of count, so we can understand the composition in the spectrum. But I'd say we don't really have a good handle on that. We see these things. We don't know whether these sources are constant. There's constant little sources going on all the time that are populating the seed population, or whether it's episodic, like you get boom, a bunch of stuff and it kind of filters out, and then you get another stuff. We don't know what that is. We know that the amount of helium-3 that we can measure at 1 AU does sort of follow the solar cycle, which makes sense if assuming the flares are creating these at helium-3, but we don't know how that's distributed throughout the heliosphere. Okay, so I'm not gonna, at the end, I have some interesting results from these, so I'm gonna skip that. So basically the newest help we have are two key things. One is Parker Solar Probe. It's now going very, very close to the sun. It's the closest thing to the sun that we've ever built. It's now just crossed, the closest I think is 13 solar radii. And pretty soon it's going to have another Venus flyby, which will lower its orbit even further. So it's going around making amazing measurements. We also have Solar Orbiter, which isn't getting quite as close. It gets into about 60 solar radii, so 0.3 AU. But it hasn't done this yet. It's going to have flybys with Venus, which are going to take it out of the ecliptic plane, which is something that we haven't really done since Ulysses. So that's going to have some really great observations. And so basically you can think of, we're going from this to taking our Parker Solar Probe and moving it all the way to just outside Hawaii. So now we actually are much, much closer to where everything is happening. And so, we're already getting lots of observations. We thought they would be a lot simpler. They aren't. I have a couple of slides here about stuff that we don't understand. The one I'm going to just show you real quick is we saw a series of SEP events. This is basically protons at a bunch of different energies. Look at 3, 4, and 5. They basically all came from this event. I could show you the movie from each event and they all look exactly the same. You have this bubble of plasma, a flare. But if I look at the helium to proton composition for these events, it looks like this. So don't mind the wiggles, that's somewhat instrumental, but basically it's kind of flat-ish with energy. But for one event, the first event, it was way down here, which is unusually low. The second event, it was really high, an order, factor of 50 higher. And then the fourth event, it was kind of in the middle. Sorry, the next event was kind of in the middle. And why this same eruption and same active region can produce these very different compositions, even though we're really close, we're at 0.35 AU, so it shouldn't be just transport. We don't understand this, and we're still trying to figure this out. And we have a bunch of other observations, and unfortunately, I won't really have time to talk about those. So I will stop there.
Great. So there are a lot of questions going on, and
Sorry, I know it's really fast.
Yeah, but part of it is what you see depends on the flare and the size of the flare, the geometry of the flare, and your observation point, and if it's associated with a CME, is it a fast CME? Its geometry, the timing, and then things happen in between.
Yeah, so that's a nice way. Yeah, that's the summary. Is basically everything depends on everything, and everything changes, and then there's a bunch of stuff that happens in the middle before we get to see anything.
And so sort of, if you've seen, is a sort of a riff on Jeff Reeves, if you've seen one geomagnetic storm, you've seen one geomagnetic storm, you've seen one SCP event, you've seen one SCP event.
Yeah, so every so often you'll see a publication that will call an SCP event the Rosetta Stone, as if we understand this SCP event, now we understand everything. But of course, it always turns out that that SCP event was special. Right. And so, yeah, everything worked out for that SCP event. But then when you go to the next one and you try and do the same thing, it doesn't work out.
So one question sort of on the clarification of the new names instead of impulsive and gradual. Why are flare events energized preferentially helium? So why are there helio events?
Right. So it's actually, so the thing that's being preferentially accelerated is specifically helium-3. So, and why is a really excellent question. So, and we don't 100% understand it. What we think is going on, and again, this sort of falls in this realm of, well, it sort of reproduces the data, but not perfectly, is that there are particular waves that are happening in the solar atmosphere that happen to resonate with the particular mass per charge of helium-3. Helium-3 has a very particular mass per charge that almost nobody else has. So helium-4, its charge state is +2 and its mass is 4. So it's, it's got a mass to charge ratio of 2 or a charge to mass ratio of half, depending on how you want to look at it. And that's common, those values are pretty common for most of the heavy ions. Helium-3 is also charged 2, but it's mass 3. So it has this 0.6 charge to mass ratio, which just happens to be sort of similar to the wave frequency of particular types of waves that we think are happening in the atmosphere. And so what we think happens is those guys get preferentially heated. They don't quite get completely accelerated, but they get to higher energies than the rest of the material. And then when you have a shock, or, well, in this case, actually a flare happen where you get reconnection and now you're accelerating particles. Basically, if something is already at higher energy, it's easier to put it up to even higher energy. So you're going, and it's easier to accelerate more of it. And so basically that's generally the idea, is that you're going to get more helium-3 than helium in this flare acceleration because you're sort of preheating the helium-3. And then the idea is that this whole process is somewhat irrelevant if you're at a CME driven shock, because all that stuff was happening at the corona and not escaping, and the shock is accelerating stuff farther away from that. It's either farther out in the corona or in the interplanetary medium, and there generally isn't any helium-3 out there to accelerate, except sometimes there is. That's the complication, but that's sort of the general idea of why you get more helium-3 in flares.
Great, and then just one more question before we take our break on talking about connectivity between source regions on the sun and our observing spacecraft. What type of magnetic mapping do you use?
Yeah, so this is a good question. There's lots of very sophisticated, I'm trying to get back to that picture. this one. So this is the most common thing. It's called the PFSS model. It's potential field source surface model. And basically what it's really not dirt, it's really relatively simple. It says, okay, outside of some surface, and they usually take that at 2.5 solar radii, but you can change that. We're assuming that all the fields are just a nice Parker spiral, right? So they just go make an Archimedean spiral because they're attached at one end of, they come out radially, but the foot point moves because the sun rotates, right? And so it basically makes these things do a spiral. Inside of 2.5 solar radii and down to the sun, they set up a potential field. And so they use this, these magnetic maps as one boundary condition, and then the source surface, there's an assumption of another boundary condition that everything kind of escapes above that. And so then they use these models and they calculate where the field lines should go from there. And that's what you get is these kind of squiggly lines. And so, you know, they don't have to go radial. They can spread out, they can go up, they can go down, they can, you know, they usually go to either active regions or coronal holes. And this is the most commonly used one just because it's really easy. It's easy to calculate that. There's tools on the web that can make this. People have mentioned SolarSoft package. SolarSoft has a routine, I don't remember what it's called, but somebody probably does, that can do this kind of thing for you. Can ingest this map and actually make these calculations for you. People like Predictive Science and people at Michigan do much more complicated mapping where they actually erupt a CME or a flare or whatever, and they look at how all the field lines go everywhere, and then they can see how those propagate out into the interplanetary medium. But that's much more computationally intensive, and so they can't just do it on a regular basis for every single event that comes along without taking lots of supercomputer time and stuff like that. So you'll see some people do that, but this is the tool that most people use. But you know, how accurate it is anybody's guess.
Great. And so since you're the next speaker, we're gonna eat into your time.
Yeah, I figured.
I just essentially shift everything by 10 minutes. And so I'm proposing that we take a break for 10 minutes, come back. For those that are at the top of the hour right now, we come back 10 after, and those who have a half-hour time zone, 40 minutes after the hour. So save your questions or type in the chat, but Christina will be back next, and we'll take the time and the office hours to be able to ask questions and
to give the whole talk over again so people can understand it. Yeah,
and
sorry about that.
Just because there were so many questions going by, if you would like to park a question someplace more permanent, I opened up a Slack channel called SEP Questions. So and posted it in the general. I posted the channel name in the general channel, so you can go there and park your questions there for office hours later. So
great.
All right.
So see everyone.
Yeah, hopefully the next one won't be hopefully the next one won't be quite as crazy.
Nick, I'm going to jump onto a team meeting real quick, but I'm going to keep my video on. So if you need something like jump up and down or wave like crazy or something.
okay, I will do that.
them, but I haven't gotten to all of them yet.
Yep. And also in terms of the textbook, a lot of the activities were based on sort of a compendium of the textbooks that Lika referred to the other day. In the chat is a link to a PDF of a new textbook that tries to integrate all of those and has a lot of the material that will be discussed this week. Okay, so you ready to go, Christina?
Yeah, like catch my breath. Yeah.
Yeah.
All right. So hopefully this won't be a little slower. There's not quite as much material in here, but you know, that's always famous last words, right? Okay. So you see that okay?
Yes.
I'm assuming that's a yes. Okay. You can't see anybody anymore. Okay, so so this is just going to talk about how we, you know, more specifically, how we create particle instruments to measure these. And mostly I'm talking about, you know, again, just about SEPs, but a lot of these techniques have been used to measure particles in radiation belts and in various other places. So this is basically, you know, what we just talked about. You know, there's all these different energetic particles in various different places. And they have basic properties that we want to measure. We want to measure the energy, or in some, you know, equivalently the velocity of the particle. We want to measure what it is, the species. Usually that's in terms of mass, or sometimes it's, you know, isotopes. More often that it's just sort of general groups like iron. Sometimes it's, you know, C and O all lumped together because we can't differentiate them. But most of the instruments now can separate those guys out. If we can, it's really hard, and I'll touch upon this. If we can measure the ionic charge state, that's actually kind of a big deal. But for high energies, it's very hard, and I'll touch on why. And then, of course, the intensities, basically how many particles are there in any given event or any given location. And why we want to do that, that was just what I gave you a whole whirlwind view on. Okay, so basically, this is the kind of measurements that we do. You know, this is the number of particles. This is adding up over a whole bunch of different instruments from one spacecraft. This is years of data, actually. And you know, if you sum it all up, you get something that sort of looks like this, where the GCRs are here. This is what we call the SEPs, solar wind, superthermal tail. And it's basically all these individual episodic events that add up to measure this. And usually we have a bunch of different detectors that have to cover this, because you're talking about something that varies over orders of magnitude, both in energy as well as in intensity. And it's nearly impossible to build one instrument that's going to cover that whole thing. So that's basically what I just said. It's a large energy range, so we need multiple instruments, which means you need to intercalibrate those instruments. So they need to, you know, if you measure, ideally you would have instruments that overlap in their energies, and then you could do the intercalibration and say, okay, I saw something at this particular energy, both of you should have measured it, and you better come up with the same answer. That's not always easy to do. We do try it. It becomes even harder if you have different instruments on different spacecraft, and the spacecraft aren't in the same location. Then intercalibrating them, we don't know whether the differences is because real differences of what they're measuring, or whether it's instrumental differences. So that can be kind of hard. As I mentioned, there's huge intensity variations, and they jump all around. And so that kind of, you can't cover the whole thing, and you can't always look at the whole range of intensity. So you have to kind of limit what you look at, because you can't, especially in space, you can't launch a huge, ginormous instrument that's going to do everything. And so you got to limit what you look at, and you got to choose what you're going to emphasize. And you sort of choose your instrument based on, you know, what the most desirable thing is that you want to look at. And then, of course, if you're putting on the spacecraft often has limited resources in terms of how much mass it can carry, how much power it can provide to any given instrument, how many instruments it has, and how much data it can send down. That actually has turned out to be a big deal, and has changed the way we've used some of the instruments. Okay, so how are they measured? So I'm going to go over sort of these different things really briefly on the ground. I'm going to talk very quickly about neutron monitors, and then I'm going to talk about the three main sort of the first measurements. I'm not going to really talk about that, but the two main techniques of measuring things in space, and then briefly talk about the charge states, just because they're important and they're really difficult, and we haven't really been doing them lately. Okay, so this is the whole talk. So hopefully I can actually get through it. All right, so neutron monitors or muon detectors, these are basically ground-based instruments, and basically the particles come in. So if you have an SCP, it'll interact with the Earth's Earth's atmosphere, and it will make this shower of all these. I know you can't read this, the resolution is terrible, but it makes all these different products of muons and gamma rays and all kinds of different nucleon and stuff. And eventually some of these things can actually reach the ground and you can measure them. In particular, we pick out neutrons, and similar technique is used for muons. Neutrons is the most common one. Basically, they have proportional counters. So, these tubes here are filled with, are your proportional counter, they're filled with gas, and they're surrounded by basically lead to sort of slow down and provide additional interactions of particles. So you have this other material that's sort of above and below it, which is often paraffin, but it can be a bunch of different things that's trying to slow down your very energetic particle. It hits the lead part, it also interacts and hopefully creates a neutron, which can then be detected by your proportional counter and then fed out to these electronics that read it, and you just sort of count it. So it's really nice and simple. So each one of these, by the way, when I go through these techniques, I'm going to tell you the method, and then I'm going to tell you sort of the advantages and disadvantages of each one. So the advantage is that these things are on the ground. They're really easy to install. They're not very complicated. You can maintain them. You can go and fix them. You can move them into different places. They're not that expensive to make. And you can put them at all different places all around the Earth. And we actually have a bunch of them in various places. And some of these are names like Oulu is a place, I think, in Finland. A lot of these other places, I don't know exactly where they are, but SOPO is the South Pole. And this is a particular event. And they often report their data in terms of relative increase. So it's sort of an increase over sort of a background level. And you can see this is one particular event. And it was seen by all these different neutron monitors, but you can see that the time profile of what they saw it varies dramatically. And one of the reasons why it varies dramatically, and sometimes they do look very nice like this one from 1956, but a lot of times they don't. And one of the reasons why they vary dramatically is because of that complicated shower process that's going on in the atmosphere, but also the path at which these particles have to take magnetically to get into the Earth and down to the ground where we can measure them. And this was a question that somebody asked, sort of, was how do these particles get in here? Sometimes they take very tortuous paths. And so you have to use a very complicated model to kind of figure out where these particles are coming from that you're detecting. And so this is kind of a hard to understand plot, but basically it's sort of the Earth, right, in terms of latitude and longitude. And these are the locations of the different neutron monitors. And the numbers 1 through 5 are basically calculations of the directions or the source location, latitude and longitude that different energies of a particle will have reached. And you can see that depending on the energy particle, they're going to take different paths and they're going to come in through different longitudes and latitudes, even though you measured them all here. And so unfolding that and understanding that is really complicated. The other thing is you don't know actually what the species is. You're just measuring the neutrons. You don't really know what created that neutron. Generally, the most abundant thing out there in SCPs is protons. So generally it's a proton that came in. So we always assume it's protons. Also, it has to have high enough energy to get through all this process. And that generally means it has to be above 500 MeV. So you're really talking the very highest energy of those of these SCP events that we've talked about. And so we don't see a lot of these. Since we've been counting, there's been 75 or something. It's not very many over, almost 100 years. Okay, this is one of the most commonly used methods. It's a stack of silicon detectors. We often call it the DE, DX versus E. There should have been a DX in here, or differential energy versus residual energy. You'll sometimes hear it called. And basically the way the process basically works is that if you have a particle and it goes through some material, and we often use silicon for a bunch of different reasons, it actually deposits energy. So as the particles, if you think of these as pieces of silicon, if the particle comes in here, it will deposit a certain amount of energy, and if it goes all the way through and doesn't lose all its energy, it will keep going until it eventually stops. And so you want to have a stack of silicon detectors such that whatever particle energy you're looking at, most of them stop in that stack somewhere. And so if you calculate, if you read out, this is why you use silicon, is, as these particles go through, they lose their energy to electrons, and we can measure that. And so you can measure the amount of energy that the particle lost in each of these different layers. And if you calculate the amount of energy lost in the layers that it passed completely through, we call that the DEDX. So you take the energy that it deposited, divide it by the thickness or the path length that it goes down, that's the DX. And then the total energy that it left in the bottom detector, and you plot that in this kind of format. So you have DEDX on one axis, basically your measurement from the sky, versus the amount of energy that it lost down here, or sometimes you sum it all up, but it doesn't really matter. Then you get these tracks. Basically, there's a relationship, and these tracks group themselves according to their mass of the particle. And so, and that just has to do with, interactions and how these things work. And you can back this. It's a very simple equation, and you can basically back this out, and you can say, okay, so all the oxygen ions are going to land along this track, and all the nitrogens are going along this track. And in fact, if you have the resolution, not only is it proportional to mass, it's actually proportional to, well, it's not only, sorry, I should have spoke. This is proportional to Z, the nuclear charge, right? So this is all, Z equals 8 particles, and this is all Z equals 7 and Z equals 6 and so forth and so on. But within that, it's also proportional to mass. So you separate out the isotopes. So if you zoom in on this carbon track, you'll see not only normal carbon 12, but you also see carbon 13 and carbon 14. And so if you really have the resolution, you can not only see, you can identify the species, meaning, the Z value, or carbon, nitrogen, oxygen, you also identify the isotopes. So carbon 14 versus carbon 12 and so on. The problem is, of course, you have to have the resolution to do this. And the big problem is that all the particles don't come in straight, right? Some of the particles are coming in at this angle, some of the particles are coming in this angle. So their path length through here is not always known. So they can deposit the same amount of energy if it has a higher energy particle that's going at an angle versus a lower energy particle that's going straight. What you read out won't look any different. So if you don't know this angle, then this all gets sort of blurred together and you can't see the difference. So this is an example of one of the instruments we have. I'll talk about the specific instruments on specific spacecraft, but this is the kind of thing is you have, an entry, and then you have particles that come in, and then there's a stack of increasing, usually thickness detectors, and you read out the energy it's deposited in all of these detectors as you go along. Okay, so so that's basically just what I said is you stack them up. You stack up more depending on how big an energy range you want to get. But of course, the more detectors means more electronics, means more weight, more power, and so forth. So you have to you have some limits. The advantages of this is, as I said, you can get elements. So this is actual data from an instrument like this, and you can see that it does really nice separation. So you could basically draw a box and say, everything that lands in this measured nuclear charge is nitrogen. And I can, this is many orders of magnitude down. So the spillover from oxygen or carbon is very little. So you can measure all these things. You can even measure isotopes, as I mentioned before. Some of these double peaks you're seeing here, this is neon 20 and neon 22. It's pretty robust. These silicon detectors are pretty, especially the thicker ones, they're pretty, solid, and they're not going to snap and break and stuff like that even during launch. So it's actually a really nice technique, pretty solid. So in order to get this isotope resolution, this is one method that was used where basically it's the same guy as this guy, but looking now kind of on top of it. These first two detectors, M1 and M2, actually have strips on them, which looks like this. So they have strips of active regions alternated with non-active regions on one side going this way and the other side going this way, and they're all read out individually. So when a particle passes through here, I can tell it passed through this particular pixel, essentially, of the detector up here. And then I could do the same thing down here, and I know what the separation is. And so now I know the angle that the particle came in. And so I can correct all those path lengths for angle, And that allows me to separate those tracks and get them really, really nice and fine. And so we can see things here like carbon 12 and 13, even though the ratio is really, really low, but you can get a really nice separation. We could see all three isotopes of magnesium, various isotopes of silicon, so forth and so on. So this is actually one of the, premium instruments for measuring isotopes for SCPs. And it's on the ACE spacecraft. I'll mention that later. Okay, so the disadvantages, the main one, of course, is these things are in space. So if something breaks, it's broken. You're not going to be able to fix it. How much of these data that you send down is heavily telemetry dependent? So in the case of this particular spacecraft, we had lots of telemetry. So we sent down every piece of information for every single particle that comes down as much as possible. And we can do all that analysis on the ground. It's really hard to do low energies. When I say low energies, I mean below about 1 MeV per nucleon or so, because in order to do really low energies, you can't make this too thick. Because remember, if the particle stops in just the first detector, you don't have these two pieces. You don't have the delta E and the E prime. You just have E. And so you can't actually, you need two detectors. So it needs to pass through completely one detector before going into the other detector. And so you can do that. You can make these thinner, but then if you make them too thin, then lots of other things start happening in terms of the interaction of the particle with the silicon. And if you don't have enough silicon there, then you can't read out the energy enough, and also it can break, and there's lots of other things that can happen. So we're actually actively working on seeing how thin we can make this. But generally you say, okay, well, it's not that thin, so I can't measure anything below, say, 1 MeV per nucleon. Okay, so the other method that's used a lot is called the time of flight method. And so basically this is a pretty simple idea. It's like you take something that you know is a certain length and you measure a start time and a stop time as the particle passes through. And basically you've measured it. These are non-relativistic particles generally. So you measure its basically the time it takes to go a certain distance, and now you have its velocity. And so that's what we call the time of flight method. The way it actually works in practice, thank you, is so a particle comes in and we have these foils. They're very, very thin. Sometimes they're carbon. In this case, they're nickel. And basically when the particle passes through, it doesn't slow down the ion, but it kicks off some electrons. And then basically you have an electric field in here that guides the electrons to what's called a microchannel plate, which basically detects the electrons, causes a cascade, and gives you out a signal. So it multiplies the number of electrons so you can read that signal better. Anyway, so that gives you, how long it takes the electron to get here. So that gives you a start time. And then the particle, the ion, keeps going and it hits a solid state detector at the end where you measure its total energy. And that also kicks off an electron, which is then guided by the magnetic fields over here and gives you a stop time. And so basically you have a start time, a stop time, and then a solid state total energy measurement. So the stop time gives you velocity. With the total energy, you can back out the mass. So now you know what the particle is. You know that it's helium or carbon or oxygen and so forth. If you measure these really, really well, you can also do isotopes with these. If you have multiple, and I don't know if that's my next slide. Yeah, if you have multiple time of flights that you kind of stick them together, this is the ULICE telescope, which I'll mention later, where they have it go through a carbon foil. So they measure the start time, and then they have it go through another one and measure a second time, and then go through all the way to the end and stop the particle and then measure a third time. And now they can do consistencies between these different timings, and they can rule out all kinds of accidental coincidences and things like that. And they can just look at the things that were consistent with one ion that goes all the way through, and so they can get really great mass resolution. And so they can get elements like this, and they can also see, so this is the time of flight versus the measured energy. And as you would expect, they group by their mass. And so you can see iron, you can see various different things like magnesium, silicon, sulfur. This, I should mention, is not this instrument. It is something that just has a single time of flight, so it doesn't do quite as well as the other one. But even with a single time of flight, you can separate out helium-3 and helium-4. And so you can do isotopes. You can do even better isotopes if you have these multiple times of flight. The disadvantages, of course, is, again, it's in space, so if it breaks, you can't fix it. These foils can be very fragile. So there have been situations on spacecraft where a dust particle managed to get in this collimator and punctured a hole in the foil. There's also been times where the foil's just ripped for, either during launch or something hit it, or who knows what happens. They're super thin. And so, so that can be, and if you lose that foil, then you're sunk. There's also been other cases where the MCPs, break or go haywire or something like that. And if you lose the MCP, then you can't measure the either start or stop time. So there's different parts that they can break that are a little more sensitive than the solid state detectors we use at higher energies. I should mention, that's easy. I lost a figure here somehow, but basically the other thing is that you can't do very high energies with this, because basically, you can't launch something that's miles long on a single space on one spacecraft and measure the particles. So you're talking about something that's usually pretty small, and which means that if a particle goes through and it's really, really fast, you're not going to measure the time of flight very accurately, or either your electronics can't count that fast, or you can't get the particles that the signals that fast, or it doesn't kick off enough electrons to actually measure. So you're basically limited to maybe a few MeV, depending on how thick this solid state detector is and a bunch of other things. You can go up to a few MeV per nucleon in this. So you can't, so this is basically a low energy methodology for measuring these particles, but it can go down to fairly low down energies. You have to be a little careful, because if it's too low, then it takes too long to get here, and it can run into lots of other problems where it doesn't kick off electrons through the foil. Okay, so let's talk about charge states. So this basically is sort of a combination of that DEDX versus E prime methodology at one end, and then at the front end, we're going to put a collimator that has a magnetic field which bends the particles, and so is tunable, so that you only let through particles that have a certain energy per charge value. And so you've got these deflector plates. So a particle comes in and it bends. Basically, if it's neutral, it's just going to go straight through and you're not going to measure it. If it's electrons, it's going to bend in the wrong way, so you're not going to see those. So if you have an ion that has the right energy per charge, it's going to follow through here, and you're going to see it come through a pass, and then it's going to do a DDEDX type measurement where it goes through a piece of silicon here. And in this case, they used an actual gas chamber. And you can get the total energy at the other end. And so then basically you get the DEDX, but you also, which gives you the mass and the Z value, but you also know the total energy. And so then you can actually calculate the charge state. This is great. It was, instrument was built, it actually used 3 of these guys that were sort of stacked together. This is the cutaway of these. And this was an instrument that was called SEPICA, and it did a great job. Now, again, you're limited to sort of lower energies because you have to be able to bend these particles. So you're limited by how big a magnetic field you can put on there, and how big the voltages and electric fields and stuff that you're setting up with your electrostatic analyzer. And so it takes a certain amount of power and weight and so forth and so on. So usually this is lower energies. It's similar to time of flight energies that we look at, but it gives this really valuable measurement of charge states. Unfortunately, this instrument stopped working about 2 years after it was launched, and we haven't put up something like that since then. Another way to basically, for the low energies, as I mentioned, it's really hard to bend those. If they're high, if the energy is too high, it's really hard to deflect those particles, right? Because the rigidity is too high. So some clever people came up with the idea of, well, the Earth has a magnetic field, and that's going to deflect particles, and so we can use that as a filter. And so if you look at the Earth and its magnetic field, basically you can see that particles with certain rigidities are going to be able to come in here. Particles with higher rigidities that are going to be deflected less are going to be able to get to lower and lower what we call magnetic latitudes, which is basically the latitude at which these magnetic fields sort of nominally hit the Earth. And so you can look at particle data from an instrument that's in a polar orbit that's crossing around all these fields. And you can see when there's an SCP event, when it goes across the top, it's going to see pretty much everybody that's coming in. As it goes down to these lower latitudes, and you know where the spacecraft is, so you can calculate its magnetic latitude, then you can see which particles start to disappear. Essentially, you don't see them anymore. And you get plots that look sort of like this. This is invariant latitude. That just means we've combined the north and south latitudes. They're a little different, but don't worry about that. So basically the latitude that the magnetic field touches the Earth. And then these are the particles. This is time. And this is just saying I saw a particle at this time. I saw particles all the way down to this latitude. And then later I only saw particles down to this latitude, and so forth and so on. And in this section, I didn't see any particles, and so forth and so on. Actually, I think that's because it was off during that time period. But anyway, and these we've identified because you've measured them through a DEDX or a time of flight, whatever. You know that these are, say, oxygen. And you can compare that to, say, what you observe for protons at a particular energy. And then you can say, okay, so I know what latitude at which I stopped seeing those particles. You can also plot it this way, which is sort of the intensity as a function of latitude. And you can see that when you're at the high latitude, say for this is iron, at a particular energy, you can see I see them, suddenly I don't see them anymore. And the same thing with oxygen. Oxygen will fall off sooner, and helium will fall off later. And basically what's causing them to fall off is their charge state or the mass to charge ratio. So you can basically say if they were all at the same, if they all had the same rigidity, they should all fall off at the same time. So I can change this in terms of rigidity by assuming some charge state and making them all land on top of each other. So if this is the cutoff as a function of energy, basically you can see the protons, are here in the triangles. And then we know the charge of a proton, it's 1. We know that the charge of helium-4 is 2. And so we can calculate that in terms of, we can convert that into rigidity and we can make them stand on top of each other. We can then assume a charge state for carbon, oxygen, silicon, and iron, and basically make all of these guys, shift them and convert this to rigidity and shift them so they land on top of each other. And that gives us our charge state. This has been used. So this is basically the shifting process to make all, just an example of protons and helium to make them all land on top of each other. And so this has actually been used a lot to calculate the charge state, and it was great. You have to, do I have the advantages and disadvantages in here? Yes. Okay. So the advantages, the big advantages, this is the piece of information which is really important to get. As you know, transport and all these kind of things are rigidity dependent. We talked about how the spectra fall off in a given SCP event due to the rigidity of the particle and how well it's confined to the shock. But we usually don't know what the charge state is. So being able to provide one piece of information, the charge state, is really a big deal. The disadvantages is if you do it with the SEPACA where you're bending things, you're limited to low energies. The geomagnetic field is really only going to give you the very high energies. The low energies, as I mentioned, it's very fragile. Lots of things that can break. And then for the high energies, of course, you have to be in the right orbit. You have to cut through all those lines and you have to have a spacecraft that's doing that. Okay, so I'm going to give you different examples. These are the spacecraft I'm going to mention, and I'll talk about, as I mentioned before, you have to make different trade-offs for different situations. So the first one is ACE, the Advanced Composition Explorer. It is still running. It was launched in 1997. It's at, it's orbiting L1. It's a spinner, and its main thing is to look at the sun. Stereo, I mentioned earlier, those are 2 spacecraft. They're non-spinners because they have imaging on them, and they're twin spacecraft and they're drifting. And then the latest ones is Parker Solar Probe. I mentioned it's going in really close to the sun. It was launched in 2018. And Solar Orbiter, which doesn't get quite as close to the sun, but eventually will tilt. And it was launched in 2020. So I'm just going to tell you the different instruments that are on there. Okay, so ACE has several different instruments. It is the Electron Proton Alpha Monitor, which I'm not really going to talk about. It's basically, as it indicated, it measures protons and helium alphas. And it does this sort of energy range. It's sort of around below and around 1 MeV per nucleon. SEPACA is the charge state analyzer that I just mentioned that broke after a couple of years, unfortunately. It did this nice medium range in here where we're talking, by the way, this is atomic numbers. So this is, mass basically. So, iron is way up here, protons and helium are down here on a different panel. And so, carbon, nitrogen, oxygen are all in this range. And then this is energy. And so this shows you the range that CPAESS looked at. The ones that are still running are ULICE, which has this funny, it's a time of flight instrument, it has this funny shape here, and CISS. CRISS measures cosmic rays, it's also still running. And then ULICE, CISS, and CRISS can all do isotopes. So this is the spacecraft, well, mock-up of the spacecraft. This is the CISS telescope. And it's, I don't know if I've got a view on that later, but anyway, this is the ULICE telescope, it's back here. And this is what it looks like. This is electronics box, and this is the telescope that's in there. It's the one I showed before. It's got multiple time of flights. It gets great data. It's still one of the, other than Solar Orbiter, is still, even though it was launched in '97, it has the best isotope measurements in the few MeV per nucleon range. This is CISS. This is what I mentioned before. It has the best isotope resolution at 10 MeV up to 100 MeV per nucleon. And it's got two telescopes. So not only can we tell the angle here, we can also compare the two telescopes, and they should be seeing the same thing because they're right next to each other, so we can do comparisons that way. Okay, stereo. It has 3 instruments that cover similar energy range. One is the Solar Electron Proton Telescope, which covers these lower energies down to below 100 MeV. 100 keV per nucleon. SEPT is even lower. That's the electrons and protons. SIT is the superthermal isotope. That's a time of flight instrument. And then the low energy telescope and the high energy telescope. These are very similar to ULICE, sort of CISS is these two things. But the problem with stereo is we didn't have as much telemetry. Remember, these guys are drifting around the sun, so we had to do a lot of calculations on board because we couldn't send down every single piece of information. So we had to make trade-offs. The other thing that we wanted to do is we wanted to use the DEDX method on protons as well as heavy ions. For ACE, the focus was on the heavy ions. We really wanted to look at the composition. So for instance, CISS doesn't really measure protons at all. It measures helium and everything on up, and it measures all these isotopes, but it doesn't worry about protons. ULICE measures protons a little bit, but it's inefficient. It's very inefficient for protons. And you had these other instruments, EPAM, that was doing the protons, so the higher ones didn't need to. But it means you don't have a high energy proton measurement from ACE. Stereo, because they're going in a very different locations, we wanted to make sure that we covered protons as well. So SEPT is 4 different telescopes. They're all basically a combination of the EDX. So these are different detectors that it's going through, and on one side it basically measures protons, and the other side it measures electrons. This magenta area here is magnetic fields that are basically sweeping out the electrons. So on this side, it's basically measuring protons. On this side, it goes through a foil transmission grid, and so it's basically measuring just electrons, and it sort of stops basically the protons. And so it's looking in 4 different directions, so it's sort of looking everywhere, and so it can get sort of a 4-pi view of what's going on. SIT, and this will look very familiar. It's basically a time of flight. But this case, because of the limitations of the spacecraft, we had to build 2 of them and so forth and so on. It only has a single time of flight. So it doesn't have quite the resolution. It can't do all the isotopes, say, that ULICE did. And then LET, again, we couldn't build this huge instrument which had all these grid, stripes on the side. So instead, what we did is we said the top detectors. So the other thing we wanted to do was look at all directions. So instead of just looking, because remember, ACE is just looking at the sun, stereo is spinning. And so in order to look at all different, be able to take stuff from all different, ACE is spinning, but it's looking directly at the sun. Stereo is not spinning. So in order to look at all the directions, we had to build an instrument that could kind of look in both ways. So what you're looking at here is the entrance, which is these guys. And then there's another guy on the backside, which is these guys. So this is looking top down. And then each one of these little separate entrances here is a detector that's split into 3 pieces. And so we read out those separately. So we know whether a particle came into A, B, or C. And then the detector that's behind it is also segmented into, 10 different regions. And then the detector inside of that is in 3 different sections. And so by doing the combinations, we can get an idea of whether the particle came in this way, or whether it came in this way, or whether it came in here, and so forth and so on. And that allows us to correct for some of these angle things. It's not as good as having this beautiful grid on, in 2 separate places where you can really get the angle really nailed down. You also notice it doesn't have as many detectors, so it doesn't go as a high energy. But it looks in all these different directions. So it can also look both at stuff coming in this way and stuff coming this way. The other compromise we did was we couldn't send everything down. So on board, the electronics classifies based on these detections what the particle is on board, which is great, except that means you can't undo that because it doesn't send you all the information. It just tells you the results. You can't undo that on the ground. So you're kind of stuck with whatever the calculation is on board. You can change the algorithm on board. You can upload new software and stuff, but you can't not do it. And so it's not quite as flexible. So you're kind of left with what the instrument can do on the fly. This little guy is Het. He does the higher energies, and he's just a sort of a simple thing. He also has some segments like this to try and get a little bit of the angles, but the angles aren't as big a deal. So he does the high energy part. Okay, Parker Solar Probe. This is one of the newest ones. You'll see that particle instrument is a little bit crazy. It is 2 pieces. It is covering this energy range, and you'll see it's kind of trying to go to fairly low energies. It's called Epi-Low is the green, and Epi-High. You'll see in this case, especially for Epi-Low, it's doing groups of ions. So CNO all together, neon to silicon, neon to sulfur all together, and then sort of iron, because it doesn't quite have the resolution. Again, we were limited in mass, power, and also in telemetry on this thing as well. So this is another pair of instruments that has to do a lot of the calculations on the spacecraft. Okay, so this is the spacecraft, and this is the shield you've probably heard about to keep everything cool. It's facing the sun at all times. This is what we call the mushroom, or Epi-Low. And these are the parts of Epi-High. So this is Epi-Low, and I'll show you how that works. Epi-High, just to be even more confusing, has 3 separate telescopes. It has low energy telescopes, or LETs. That's the red ones here. One of them is double-ended, so it looks in both directions, kind of like LET on stereo. One is just single-ended. It looks orthogonal to this guy, and so we call this LET A, LET B, and LET C. And then there's Het, which just is 2 double-ended, so it's got Het A and Het B. So the nomenclature starts to get a little confusing, and I apologize for that. Okay, so the mushroom, Epi-Low, is basically 8 wedges of time of flight telescopes. And each wedge looks a cross-section like this, where it has 5 different, actually it has 10 different telescopes. You can see that you only sort of see 5 here, but you can see that there's 4, and then 2, and then 2, and then 1, and then 1's at the top. So it basically ends up being 10 on each wedge times 8 wedges. That's 80 different time of flight measurements. And so a particle can come, and these are little tiny things, so you don't get a lot of angles. So basically, if it goes in this one or it goes in this one, that kind of gives us the angle that which it's coming in. We know where it hits the solid state detector, and then it does the usual kicking off electrons, which are measured at various different places on the stop detector here, start and stop detector. So we measure the time of flight of the particle and its total energy, and so that gives us the element. And then by having 8 wedges, you can look in all these different directions, and you can separate it out basically, whether it's coming in near the top or on the sides and where around. So it's pretty complicated, but the basic idea is still time of flight, which is basically the same kind of thing we've done before. So here's LET. It's basically very similar to LET that we talked about on stereo. And Het, it's got these segmented detectors that are all stacked up. It doesn't have that fan that stereo had, but it just sort of has one of those. But it has it looking in both directions. So particles can come either in here or they can come in here. What part of the detector they pass through is read out, so you can get some idea of what the angles are and correct for that. It doesn't really do isotopes. It can separate out helium-3 from helium-4, but that's pretty much it in terms of isotopes. And basically head is just more silicon, so it does the higher energies. The thing about this guy is that, and this also happened on lead, is that because we also want to measure protons, and protons can be much more, higher density, or much higher fluence, orders of magnitude higher than, say, oxygen or carbon or whatever like that. If you have a big event, it can overwhelm this detector, and so with just protons, and so then it can drive the live time, which means the instrument cannot count fast enough. And so we actually will shut off certain parts of these detectors so they're insensitive to protons and helium. This instrument also measures electrons, but I'm not going to go into that. So it basically raises the threshold so those guys can't trigger these detectors. And now we can just focus on the heavy ions without driving the live time really low. That also makes things really complicated. LET does the same thing, but that's how we manage to cover these big intensity ranges. And that's particularly important for Parker Solar Probe, because as you get closer to the sun, things start to get bigger and bigger, just because they haven't diffused out by the time they get to 1 AU. Solar Orbiter, this is the last one I'm going to go over, and it basically has a bunch of telescopes, again, to cover this whole range. STEP, sort of like on wind, it's basically just does protons and electrons. The electron proton telescope does just what it says, electrons and protons over this energy range. It's a pretty big energy range for protons. And then you have CISS and HET, not to be confused. This is a different CISS from the CISS that's on ACE. I told you we can only really count to 2 or 3. We can apparently only make the same number of acronyms with the same letters. And so it covers this sort of range, and then HET comes the higher energy ranges. You can see that there's some overlap, but there's areas where they don't overlap, and that's a consequence of this being a time of flight and this being a DEDX. This commonly happens, that you get this gap here. And so you can't really intercalibrate them as well as you can down here. Or for, when I say down here, I mean for these elements. Okay, so we'll just really quickly look at what they look like. This is the spacecraft. It's got its shield over here in this particular projection. This is where the instruments are on the spacecraft. This is what they look like. This is CISS, EPD is in here. EPD is the whole thing. EPT is over here, STEP is over here, HET's over here. I know it all looks very confusing with lots of wires and stuff. Anyway, so STEP is just a simple deflection thing. It's the same thing as before. You've got particles, they got to go through a narrow thing, and then they are measured by a solid state detector. This is actually pixelated here, so we can actually just see where on the detector. So it's almost like having lots of tiny little telescopes all next to each other, and so you can look at whether things are, get a sense of anisotropy and things like that. EPT is just pretty much the same thing as SEPT on stereo. It's basically does, electrons on one side and protons on the other side, and is basically just measuring the energies as they come through. So it's pretty simple. HET is just a same sort of thing. It's a silicon based detector, so it's got a set of detectors on either side. Particles can come from either way, and they stop basically in this region through a set of silicon detectors, and they're segmented, which again gives you a sense of angle and things like that. So you're seeing a lot of the same techniques happening over and over again. CISS is basically ULICE with multiple times of flight. They've changed a little bit in terms of the spacing of the time of flights, which gives them, just coincidentally the way it works, even better resolution. So CISS actually does incredible isotope observations, and it's super sensitive. So it's getting some great data, especially for these helium-3 rich events. Okay, so this is actually my last slide. So here are some considerations of using the data. And this is what I talked about, this mode of the instrument. Some instruments, ACE didn't really have any modes. It was just up there all the time, and it's measuring stuff and it's sending everything back. But as I mentioned, LET on stereo, but also EPI high, the LET and HET instruments on EPI high on Parker Solar Probe, we do these modes to be able to handle big fluxes of protons. And basically, this is a cutaway of the stacks of silicon. And what the light blue is when it's in sort of normal mode. And you can see the dark blue is we've raised the thresholds on certain segments of the different detectors. So that now when protons come through here, they don't actually get through, protons of a low enough energy, they don't actually get through here and we don't measure them. Or they get through here and we don't actually measure their energy. And so the instrument doesn't waste time processing it. But the heavy ions can still get through here because we set the threshold such that the heavy ions are still detected. If it gets even bigger, we go into DT2, which raises even more of the thresholds on raises the thresholds on more of the detectors. So you're cutting out even more of the protons and helium that you're sensitive to. And if we go all the way to DT3, it basically means we're not measuring protons at all in terms of this instrument. We're going to just focus on all the heavy ions because the event is way too big. We'd just be swamped. Now, the one exception is these tiny little things, what we call the pixel detectors. They're little tiny squares on a couple of different detectors that we don't change the thresholds on. And so technically protons can still be measured by these little tiny pixel areas. So we have some idea of what the protons are. We don't measure very many of them, but there's so many out there, we don't have to measure very many of them to characterize the variation. So in DT3, we sacrifice a lot of the information about the protons, like the whole spectrum, only measure a couple of energies, but we allow the instrument not to be swamped and lose all our data. So we basically are capable of still measuring the heavy ions. This lifetime is basically what I'm talking about is, so instruments that don't go through this mode, if they hit a big event, the lifetime of the instrument, meaning the instrument cannot count fast enough. So it slows down and it spends more time processing the things it does, which means there are time periods where it's, quote, not live. And so you can see the live time sometimes when a instrument is working really, really hard, the live time goes way, way down, which means you're not really getting as good a sample of the material as you think you are. Pile up is when multiple particles hit the detector at the same time and the detector thinks it's a single particle. So you get more energy than you really should have per a single particle. When we do processing on the ground, like we do for ACE, we can detect this pile up pretty quickly. We can kind of see that it's not consistent. We can see, what things were hit when. If you have to do it all in space, you don't have as complicated, you don't have as clever you don't send a person up there. So everything has to be done by the computer, and the computer's only as clever as you made it, and we're able to do it within the small amount of code space that you had. And so it doesn't do as good a job with this pile up. But there are some methods to kind of, tease that out. But that can create a general background, which means you're not as sensitive to the lower intensity. Background in general, you can have noise in any of these detectors. You can have cosmic rays that are coming in from the side that are triggering these detectors. So depending on how much you shield it and what you do, you can do various different things to bring down that background so that you can measure things better. The other thing is the spacecrafts aren't always pointed in the direction they're supposed to be pointed. So Parker Solar Probe in particular and Stereo, they spin every now and then to calibrate the magnetometers. And so when that thing spins, we're suddenly pointing in different directions that we thought we were. Also, Parker has to be tilted. This is to actually talk to it, so that because the antenna is just on the side. So they actually have to tilt the spacecraft a little bit. So now we're not looking in the direction that we think we're looking. So you have to pay attention to those kind of things, especially if the distribution is not isotropic. Stereo in particular, since their antenna is on one side, when Stereo A went behind the sun, they had to actually flip the instrument, the whole spacecraft, 180 degrees so that its antenna was still pointing towards Earth, which means all the things that we thought were looking this way are now looking this way. And so all the telescopes that we've labeled sort of looking, along the Parker spiral are now not looking along the Parker spiral. And so again, you have to be aware of the conditions in which the spacecraft are taking data. And
10-minute warning.
Okay, well, I'm basically done. And I guess I forgot that I had figures of this. This is a plot of live time. So you can see this in an actual event. And I think this is from ACE, where the live time up here, it's normally counting in, the 249 seconds or something. A big event came on and the live time went almost to zero, which means that the instrument is spending more of its time analyzing things than it is having particles, detecting new particles coming in. And then the event eased up and went back up, and then another event in the lifetime went down. So it basically means your statistics go to crap when you're down here. And so that's why we built stereo, is to sort of mitigate this situation and change it. So this is the background issue that I'm talking about. This is helium-3 to 4 mass histograms from a bunch of different energies from a bunch of different spacecraft. This is a function of time. Basically, you can think of it as, so these are from ACE. This is helium-4. This is the track here. This is helium-3. And you can see blobs of helium-3 nicely separated from helium-4. That's a really nice helium-3 rich event. This is just a different energy, also from ULICE, higher energies. You can see this event still shows up. This is from CIS. We don't separate those out quite as well as you do in ULICE. And you can see that, those events don't really show up here. This is from stereo, where the resolution is not as good, but you can see, events where you have helium-3. And this is from Parker, where the resolution is also not great. And so the type of background you also have to consider is, if you get a really big event that's, say, big in helium-4, that Gaussian, or basically peak, can spill over into the mass of helium-3. So if there's helium-3 here, you're probably not going to see it, because what you're really seeing is the tail of the helium-4. If you see a nice gap in between here, those two things are real. But if you don't see a gap, then that's probably background, which means you're probably not seeing helium-3. So even though the instrument, like these things, as I mentioned, classifies it on board, the instrument will tell you there's helium-3 here. But if you look at the data, you will recognize that that's actually background and there's not any real helium-3. Okay. This nice thing had to do with the pointing. This is Parker Solar Probe data, and this is the LET data, and it's just looking at different sectors, but don't worry about that, because they're all seeing the same thing. So basically, the counts, this is basically protons, come in, and then they start to do this crazy wiggle thing. And this should always be your first reaction when you look at data. When you see something that looks crazy, you go, what's wrong with the instrument? Or what is going on with the spacecraft? In this particular case, don't assume it's actually real. And the fact that all the sectors, basically every direction we looked at, was all doing the exact same thing. Basically, it turns out we went back and looked at Parker, and they were doing a mag roll. So basically what's happening is the spacecraft is rolling, and the distribution is anisotropic. So every time our field of view passes through the peak of this distribution, you see it go up. And then as it rolls around the other way, it goes away. And then it rolls up and it goes away. And if you plotted the period of the mag rolls, they will line up exactly with each single one of these peaks. So these are the kind of things that you can see in the data, and you have to immediately question what's going on. Could it have been real? In this case, definitely not real. All right, that's it.
Great. Thank you very much. And so if you could just raise your hand, and Christina, feel free to call as the order of questions come in.
I see Andreas has a question.
Yeah, one question regarding the lifetime. Is it like a limitation of how often you can read out the silicon, or is it like limited processing power of the spacecraft?
Yeah, so it's a limiting processing of the instrument. So it's usually not the limitation of how fast you can read out from the silicon, though there is some issue with that, right? You've got to shape the signal, and it has to last for a certain amount of time and all these things for it to process. And if you get another one in there, then it can not register. But mostly what happens is, especially on board, like for stereo, where it's doing analysis of all those signals on board, and it's got to classify all those. It's got to take all the signals that it's getting from all the different stacks of silicon, and then go through an algorithm and then say, okay, I need to increase this counter, or I need to increase this counter, or I need to classify it as this thing. And while, it can do that pretty fast, while it's doing that, it says, hold off, I'm not paying any attention to anything else that's coming into the instrument. And so if it's got to do that a whole bunch, because it's got a whole bunch that are coming in, and if they're really complicated because they're going really far in the detector and it has to analyze lots of signals, then it takes more time. And so you end up just sort of driving the instrument too hard, and it can't keep up in terms of its processing. So it's mostly a processing power.
where I think I would assume the count rates are higher when it's closer to the sun. This is probably less of a problem because there's stronger computers now on it, which.
Yeah, you would like to think so, but NASA has a habit of sending its most basic and not very, capable computers on its spacecraft for whatever reason. I mean, partly because it has to be radiation hard. It has to be able to survive launch. It has to not be, oddly, the SCPs we're trying to measure can also cause damage in the spacecraft and the electronics, right? So it has to be all protected, and that has weight and power limitations. I will tell you that the bane of my existence right now is that the computer, this is the spacecraft computer now, on Parker Solar Probe was designed such that it does not have enough processing power that it can keep the instruments on and making measurements when it is transmitting data to the Earth. So every time we want to download data, they shut us all off, which makes me nuts because nobody else does that. Every other spacecraft can multitask. Basically, it can send down data and keep data coming in at the same time, but Parker does not do that. And we've asked them about that, and they say we are already driving our computer processing to 99% of its capability, and we cannot add that other additional load onto it. So you'd think they would, I joke that my phone has more processing power than some of the stuff that's up in space.
Yeah, and if you think about the electronics for pulsite, if you want to count every particle coming
everything
in,
that comes in,
it's a RC circuit. So if you can get down to a microfarad type of capacitor and such, you can get down to nanosecond-ish type of thing. So that is really the limit, and not necessarily fast processors per se.
Yeah. So
great.
there's lots of bottlenecks. I don't know what order these came in. Alicia?
Yep.
Sorry, was that right?
Yeah, that's right.
Okay.
And just a basic curiosity about how this particles after detection, if they're flushed out or diverted somehow, because when there's like impulsive events and you have so many particles coming in, for example, in the time of flight method, how are they dealt with after that detection so that more
Right.
particles can be detected?
Yeah. So the particles that we detect generally stop in the instrument. So one of the key methods in order to measure the total energy of the particles, it has to stop in the detector, right? So usually in the solid state detector, it has to, there are higher energy particles that pass all the way through, and basically if they pass all the way through, we never get a measure of its total energy because it will pass all the way through, leave some energy and keep going. Now, a lot of times the way these things are mounted, it keeps going by running into the rest of the spacecraft. So, it'll stop in the spacecraft. But those particles generally we don't analyze because we don't have enough information. There's some techniques that we have to try, we call those penetrating particles. And there's some techniques that we have to try and recover enough information to identify them. And that will take you to slightly higher energies. But generally those measurements are not, as well calibrated, and they're not as good, and they have limitations on them. So basically you can think of every particle that we actually measure is gone forever. It'll never reach another spacecraft. It stops at that spacecraft, but there's so many of them that we have plenty to go around. Everybody can share.
Okay, thank you.
Yeah, Angelo.
Hello. I wanted to ask if the interactions between among the particles will affect the measurements eventually, or if they are negligible.
Yeah, so space is really big and the densities are really low. So generally the particles do not interact. They don't run into each other. So now you can get interactions with material in your instrument. So like if it doesn't come down the center of the instrument and get detected in your time of flight or your spacecraft, but it hits the walls or something, depending on the particles, sometimes you can get interactions there, which will create a secondary particle. Generally, that's not going in a direction that we're going to actually measure. That's why we have these sort of collimators to make sure things are kind of going straight. Or we have deflection systems to kind of sweep out electrons and make things go where we want to go. So generally, we don't see them. The one exception I will say is, Parker Solar Probe is kind of interesting because it has that big shield, it's a carbon shield in the front of it to keep everything from burning up when it gets close to the sun. And we have noticed that it is possible for particles to interact with that shield and create additional particles that we can detect in our instrument. Now, usually they're high energy things, they're like neutrons, or they're actually X-rays, which we can actually oddly detect in our instrument occasionally. So it's usually not the same kind of thing that you're normally looking at. And since we have these different measurements of different energies in the stack detector, we can try and make sure that there's a consistency. So if you say, okay, this is a carbon atom and ion, and it went through, 5 different detectors, I can use this DE, DEX versus E measurement with different combinations of that delta E. So I can use just the top detector or a couple of detectors or 4 detectors, and that gives me different paths, but I know they all have to be the same particle. So I can do a consistency check to basically say, are all these measurements consistent with one particle of that, mass going through? And so if it's not consistent, then we often just throw it out and we go, we don't know what that is. We're not going to worry about it. And then there's ways to normalize the fact that you're not measuring every particle, which I won't go into. But so, these interacting particles, we can usually ignore them, but they do, they can contribute to the background.
Okay, thank you.
So we ran into our office hours and lunch break, and to keep us going, I want to see if Nick is around. Do you propose?
He's getting lunch.
Okay.
No, I don't.
I'm here. I
Do you
have
propose at the top of the hour for those on hour zones and the bottom of the hour? So a 1 hour from now break, or 50 minutes?
okay, I think 50 minutes is fine. What do you, unless people are really concerned?
So I propose that those that need to take a break, this is the time, but we'll be on for office hours, and you can continue. Those who had their hands up can stay on.
Keep asking
We'll continue
questions.
talking. But for those that are dropping off, we'll see you in 50 minutes at the top of that hour, East Coast time, 1 o'clock. Great. So sorry to kick everybody's hands down.
Yeah, and we will get back. We immediately get back to office hours. So
an hour, and then also office hours.
yeah, and so Rehab, you, if you have a question, I think you're up next.
Yeah, please. So
Yeah, sure.
I'm sorry, but I'll get you back to the lifetime part. If the lifetime is, we can say that it is the processing time for the instrument to process a bunch of electrons or bunch of data, or sorry, bunch of particles, till it gets saturated, and then it doesn't look at the other particles, and then it restarts after it analyzed the first bunch. So wouldn't it affect the measurement during the severe events, especially, or what?
Yeah, so lifetime, you can think of it as sort of exactly what it's called. It's the amount of time the instrument is live, right? So, you can accumulate a 1 minute time period saying I'm measuring and giving you the number of particles I saw over 1 minute. But in reality, the instrument is not live for that full minute. So you have to account for the fact that the instrument is actually only live for maybe 50 seconds out of that 60 seconds, right? So that's one thing. So that's just in general, when everything's working smoothly, you have to account for the fact that the instrument is never 100% live, right? It always has to take a little bit of time out to process and to do some stuff. And during that time, it's not counting particles. Now, the problem is that when you get a really big event, right, the amount of time it needs to process becomes bigger and bigger, and it cuts that way down. So your live time, instead of 50 seconds, goes down to 30, goes down to 20, goes down to 10. And your question is, the problem is, right, is that when it goes down to 10, you're in a big SEP event, which is exactly the thing that you want to be measuring, right? And
Yes.
so, and the problem is now you're not measuring it as well, right? So that is the problem. So you can do a couple of different things, right? You can, and these are the trade-offs that we talk about. So for LET and Parker Solar Probe, because it's going in closer, so we thought we were going to see some really big events, you can basically start to choose which particles you're going to pay attention to and which particles you aren't. And the way that we do that on stereo and Parker Solar Probe is we raise the thresholds of the detectors so that if a proton hits that detector, and also we raise it high enough that even a helium that hits that detector, it won't be counted by the instrument. So the instrument doesn't have to process those things, but you are losing that information, right? Now you are not measuring those particles at that particular energy, right? You'll still measure maybe the higher energy ones, depending on where you put your threshold and how many of them, but you've got to make a decision as to what you're going to do. The other way of doing it is you can make your detector really small so that it doesn't get overwhelmed, because, you know, now the aperture is only this big instead of this big. Well, they're rarely that big, but say it's really, really tiny. And so you're only measuring a few particles anyway. And so then when lots and lots of particles come, you don't get overwhelmed. Well, the downside there is that when there's really low intensities, you're not measuring very many particles, right? So you're basically giving up the smaller events. You're saying, I just can't even measure those, right? So this is the problem, is you can't measure everything that you want to under all conditions. So you've got to make some trade-offs as to what you want to do. And so you could let the live time go way, way down and say, okay, well, I'm still measuring the guys I want. I'm just not measuring very many of them or for very long, which could be fine, right? So instead of 50 seconds worth of data, you've got 5 seconds worth of data, but and maybe that's fine. You still got lots of statistics, and you can say, okay, during that 5 seconds, you know, I can calculate what the intensity is, and that's fine. But you're assuming that things aren't changing in that other, you know, 55 seconds. So I get a 5-second sample of that minute, but if things change dramatically in that minute, that sample I get is no longer representative. You know, I can say what it is, but it may not actually be representative of what's happening during that full minute. So for instance, you can also integrate if you want to get to really small events, sometimes we integrate over an hour, right? So we just count everything that comes in an hour. Well, that's great, but if things are changing a lot in an hour, you've just got one measurement, you're maybe not capturing, you know, what's changing very much in that time. So it's always a game of trade-offs. In ACE, we decided not to even try and measure protons. We just said, we're only going to measure heavy ions. They never get to intensities that are such that we really overwhelm the instrument too much. That actually turned out not to be true. As you saw in that plot, the lifetime still went way, way down during one of these really big events. So, you know, and all of this has to be, because you're doing it in space, you have to make all of these trade-offs and plans, and based on what you think you know before you send the thing off. And so you have to figure out what you're going to do, and then you send it off. And then if it turns out you made the wrong trade-off or you didn't account for something, then if you're really lucky, your software is malleable enough that you can change it and you can upload some new programs to handle it. If you're really unlucky, you can't. We couldn't do that on ACE. So what we did is, for like stereo, we made everything a free parameter, basically. So we could change all kinds of things. On ACE, we hard coded a lot of it. But you weren't doing the analysis on board for ACE, you were doing it on the ground. So you could kind of handle a lot of that stuff. On stereo, it all has to be done on board. And so, you know, we tried to make it as flexible as possible, but there's still just limitations to, like, you know, the thickness of the detector you picked. That's just what it is. You can't change that. So you have to kind of go in with what you think you know and what you think you're going to see. Sometimes you get it right, sometimes you get it wrong. Most of the time we get it right, thankfully. So
Thank you so much.
Yeah, sure.
I have a question about detectors. So how does the usage of solid state detectors and scintillatory detectors differ? And when do we prefer one of those? Is it energy range or the fluence or some other physical constraints?
Yeah, so we generally use silicon solid state detectors. I think it's because we know a lot about the properties and we know a lot about the interaction of particles and how they behave in that material. And so I think that's the main driver. A lot of it is, so I will tell you that NASA is very risk adverse. So if you tell NASA that I'm going to build an instrument that's going to use some totally new detector that has never been used before, and it's going to do a great job, they're going to say, yeah, not so much, go launch it on a rocket or something that we don't care about if it breaks and doesn't work, but don't put it on our billion-dollar spacecraft, because if it doesn't work the way you think it's going to work, then we lose that measurements. And so NASA is very, very keen on what they call heritage. So you basically have to say, I've essentially built this instrument before. I can show you it works great. I'm only tweaking things around the edges. So we basically don't change the detectors. We always use silicon. We change how thick they are. And we do tests, and we've got a couple of grants to like try and make really thin detectors, which allows us to go to lower energies. But the question is whether you can make them uniform thickness and a bunch of other, manufacturing issues. But we have to kind of show that works through a lot of calibrations and a lot of testing and stuff like that. And we have to point to that and tell NASA that, yes, we've done all this stuff and it's not going to break when we use it in an instrument. And so they'll let us do that kind of thing. But if you came up with a completely different detector, material, they're probably not going to be happy unless you've already sent it up on some low cost mission or a CubeSat or something that didn't cost them a lot of money first, that you can show that it really works and it can survive. So I think, some of it is just, this is what's been done in the community for decades, and we know a lot about it, and we know how it works, and we know how to do the electronics and things like that. So that's one of the main reasons why you use silicon. The time of flight versus, using the DEDX thing is, as I mentioned, is mostly an energy thing. What energy range are you trying to go to? Does that sort of answer your question?
But what about scintillatory detectors? They're being used as well.
Yeah. So what do you mean by, like, what exactly are you talking about?
No, I was just asking when we are using the solid state and when we use that second kind that's using spot and scintillation. So when the high energy particles gets into the detector.
So there aren't really, so there aren't many. So there aren't a lot of SCP instruments that are using scintillating detectors. The CRISS instrument actually uses scintillating fibers. So as I mentioned, the CIS instrument on ACE has those stripes on the top and bottom of the silicon detectors at the front to tell you where it went through. CRISS actually has a bundle of scintillating fibers on top of theirs, but they're doing higher energies. They're doing galactic cosmic rays, right? So they're doing GCRs, and they have a bed of scintillating fibers that are going in multiple directions, and the particle passes through there, and they read out each of those fiber bundles to see where it went through, and then they can tell what angle it's going at. I think the problem with scintillation is it generally has to respond to higher energy, and it requires a lot more electronics to read things through. So you're really limited so when you're building something that has to be, this big to be on a spacecraft, so CRISS is maybe like this big or something, and we can't put anything that big on most of the spacecraft that are going up these days. They just don't want to carry something that big, that heavy, and taking up that much power. Now you do have things like big instruments that will go on balloons, right? Because the balloons only go up so high, and they can take really massive, heavy things. There is the AMS instrument, the Alpha Magnetic Spectrometer, I think is the acronym. It's on the space station. That thing had to be delivered, with a shuttle. I think it went up on a shuttle or something. That thing's massive. It's huge. It's sitting on the outside of the space station. You would never be able to send that up on a spacecraft. It has huge magnets. It has scintillators. It's doing all this stuff, but it's mostly also, it's just looking at higher energy stuff. It's looking at GCRs and things like that. It's doing great, detailed detections, but it's all in the hundreds of MeV per nucleon and up range. So it's looking at something completely different. But again, you couldn't put it on a spacecraft like, Parker Solar Probe or something. It's just way too big. So I think that's generally, we don't generally use the scintillation technique so much, just because, it ends up being big instruments that require a lot of electronics and a lot of weight and power. If that makes sense.
Yeah, thank you.
Yeah, sure. Mohammed.
Hi, thanks. So I have a question about the lifetime. So if a detector has a lifetime, let's say for 1 minute, does it mean that it keeps reading or taking measurements for a minute and then take a break for 1 minute and then continue for another minute? Or
So-
it keeps...
Yeah. Yeah, so basically what it is, it's sort of like that, but it's not like a minute on, minute off. Basically, when we report the live time, so we usually have that in like data streams and stuff. You have one of the things the instrument measures is how long it's live. And so if you're integrating over a minute, basically it will take a little sliver of that minute to process. So you'll have an integration, so it'll be live for 50 seconds, and then it'll be off for 10 seconds, and it'll be on for 50 seconds, and it'll be off. Now, sometimes things can kind of come in and muck up things during that off time period. So sometimes it's not quite live or quite dead and not live. I don't know how to, what the opposite of that is. So, even that you have to, worry about things, because a lot of it is response to the electronics, and sometimes there's a little tiny time window in there where the instrument reports that it's not live, but it could actually detect something while it's reading out something. So it's mostly like the detectors themselves are still detecting and they're still sending out their signals. It's just that the processor that's reading those signals and analyzing is basically saying, hold on a minute, I'm ignoring you for a couple of seconds, and then I'll get back to you. So it's really sort of an on-off thing, but it's usually, the live time is usually small, so you're sacrificing a small time period for the integration. It's basically what it comes down to. But yeah, it's sort of, I hesitate to call it off, because it's not like the instrument shuts down, right? It's just that the processor ignores the signals that it's getting from the detectors during that time period because it's busy doing something else.
But during the processing time, the detector doesn't count actually, right? Like it doesn't record these measurements during the processing time.
Yeah, so I want to make sure we're using the terminology the same, because some people say the detector and they mean the whole telescope. Some people that say the detector and they just mean that one piece of silicon, right? So the pieces of silicon, they're sending out signals all the time. Whenever a particle goes through, it sends out a signal. You can't stop that. It's doing that, right? That gets to a piece of a wire, and which goes to a piece of electronics, which takes that signal and it shapes and it does a bunch of things. So when the instrument is not live, basically that signal goes to the processor, and the processor just doesn't register it. It just says, I'm busy doing something else. So it doesn't register. So the particle is still interacting with the detector, and the detector is still sending out a signal, but the processor is ignoring that signal essentially during that time period. Does that make sense? Is that more clear?
Yeah, now
A little
yeah. Thanks so
Okay.
much.
Yeah, sure. Kentucky.
Yes, hi.
Hi.
Thanks for the nice talk. I wanted to ask about the calibration. When you do the calibration, when the spacecraft is moving through different kind of background plasma, like how much it is challenging and how we can address those challenges.
Okay, so yeah, it's very challenging. We try and
Yeah.
calibrate the instruments on the ground before we put them on the spacecraft as much as possible. However, we cannot create the same environment that it is going to experience in space on the ground. So for instance, we usually take our instruments to accelerators, like the high energy physics accelerators, right? And we put them in there and they give us a beam of particles, and it's usually of a particular energy or an energy range, and it's usually a particular composition. It could be a silicon beam, it could be an iron beam of ions and such. But there's only so many different compositions that they have for those beams, and there's only so many different energies they have, and they can't aim it at different angles at your instrument, right? And they can't give you generally can't give you more than one element at a time. So sometimes what we do is we put a piece of material, usually a grid or something like that, in between the beam and our instrument, so that when the particles hit that, they interact and they actually create other particles. So if you put in an iron beam, it fragments and you get all kinds of other iron, but you also get some silicon and some argon and calcium and all these other things. And so then your instrument gets hit with all these different particles, and you can see how well it can differentiate between those two. And it changes the angle a little bit, but not much. And so it's really hard to calibrate the instrument's angular response. Sometimes you can, if it's a small enough instrument and you put it on a rotating platform, you can kind of rotate it a little bit, but you can't do all the angles at the same time, which is what it's going to see in space. The other thing is you usually can't get to the intensity levels that we're used to seeing in space. So if you have a huge SEP event, you're not going to mimic that on the ground. So it's actually very hard to, on the ground, drive the instrument hard enough to see what it's going to do when it's getting bombarded by all these things. So like for LET on stereo that has these different dynamic thresholds, we have an algorithm for when it should change from one threshold to another, right? So if the intensities get high, the instrument knows and it shifts to the other dynamic thresholds. And that's a setting that we have in the software that we made changeable. And we tried to test it on the ground, setting the setting really low to sort of force it to go into the different thresholds. But again, it's artificial, right? So you're having it when it's not really being that overwhelmed, right? Whereas in space, it's going to shift when it is being overwhelmed. And so you can't really account for all these things. So basically we try and do the basic, make sure that those tracks that we create are sort of falling where we think they are, so that the software can say, okay, it's in, I can draw a box around that and I can count those. And we make sure we have the box kind of in the right place, and we can do those kind of calibrations. But inevitably, when we've launched the thing and we first turn it on, it almost never does exactly what we think it's going to do. And so we then have to wait for an SEP event and look at the data that come down. And then we almost always end up tweaking things and moving, like moving those boxes slightly or changing the level at which it goes into dynamic thresholds. And that's why we try and make everything commandable, is so that we can change those things on the fly. But, it's kind of hard because you have to have an SEP event, and those don't come along every day. And so, for instance, stereo was launched into deep solar minimum. It was like, we saw an SEP, we were lucky. We saw an SEP event right after we launched. And so we were able to do some calibration and fix things then. And then we saw nothing for like 3 years. And so then it was sort of like, okay, well, when we get an SEP event, we'll sort of figure out what other aspects of the instrument need tweaking. So you end up calibrating it some on the ground and then some in space. And, it's kind of tricky. Does that answer your basic question?
Yes. And I also wanted to know, like, how do you do the background subtraction in such cases? Like, because like the background plasma is like varying very much, like when the spacecraft is moving. And in that case, like do you do like at what position the spacecraft is, and then you decide like what background subtraction we have to do? Or there is like generalized a thing as such for this thing?
So the background plasma is usually at low enough energies, we don't have to worry about it. We're not measuring the background plasma. For the high energy particles, the background is pretty low. Now there can be background due to your detector not being, or galactic cosmic rays. Galactic cosmic rays create a background, but that's pretty constant with space in the areas that we're going into. And it also is fairly, it changes very slowly. So, over the course of an SEP event, the GCR level and the background it creates is not going to change dramatically, right? It'll change over the course of, a year or something like that, but not over days. So, and then the instrumental background, it's something that you just, you find a quiet time period and see what your instrument is doing. And then you say, okay, well, that's the inherent noise in the system. And so you can calculate that. And that's obviously not going to change depending on where the spacecraft is, things like that. So, but the background solar wind and the way it affects our data is in the transport of the particles, not in terms of affecting our measurement of the particles. It's affecting our interpretation of, what started and what we measured, but it's not affecting how well we measure that, if that makes sense.
Okay.
Sort of.
Yeah.
Okay.
Yes. I have one more question about the propagation of SAPs. Like, I just wanted to ask, like, they are restricted in the equatorial plane, like along the Parker spirals, or they are just going everywhere?
They go everywhere. Yeah. So
okay.
that was one of the plots that I went by really fast. Ulysses was in a polar orbit. It actually went out of the ecliptic plane. It went out to Jupiter and got a slingshot and then went in this big polar orbit. So it went over the poles of the sun. And there were times when the plot I showed had Ulysses, I don't know, it was at 60 degrees latitude or something. It was way up here. And then there were still, you know, we had instruments down at L1 and we had an SCP event, and Ulysses saw a really strong SCP event, just like the L1 things, which means that particles were getting all the way up to 60 degrees.
Yeah,
And the
okay,
question is,
okay.
how does it do that? Because,
Exactly.
you know, we always
Yeah.
think of the Parker spiral as being nice and uniform and in the ecliptic plane. But if you look at those hairy ball images of the sun where it's got, you know, field lines going off in all directions, right? Because you're looking at it, not down it. You'll, you know, at the poles, the field lines are going out and then they do this and they go out. But the question is, how do you get particles up there? And I would say
Exactly, yeah.
that is an unanswered question, but they definitely get
Okay.
there. We've seen them.
Yeah, because I just like saw one recent event where the event was backsided, but the particles were detected from the earth side of, so yeah.
Yeah, that's a big question. So yeah, there's events that happen on the backside, but somehow the particles get all the way around and we end up seeing them as well. And so explaining how that, and sometimes it happens really fast. And so explaining how that happens is definitely an open question. We don't understand that very well. So.
Okay, thank you so much.
Sure. Rehab.
Yeah, it's me again. So
fine.
now we're talking about the background solar wind and how you differentiate. So I just it's not a question, like I'm wondering, so how we differentiate between the SEPs event and the high speed streams, or what is the difference between them? Is always the SEPs are associated or resulted from solar flare or a CME, or yeah, that's it.
Yeah. So yeah, so I understand why this is confusing, and there's a lot of acronyms that are being thrown around all over the place. I apologize.
They
for
all
that. Yeah.
mean solar wind.
I know. Yeah, it is complicated. So one thing to think about is the solar wind's there all the time, right? It basically, well, there's a paper on the day the solar wind stopped or something where the densities went to 0. It's a little weird, but generally the solar wind is always there, right? And it's going faster or slower, but it is always coming out. Now, where it's coming out from the sun, whether it's coming out from a coronal hole or whether it's coming out from a helmet streamer or, you know, active region, all that stuff is, you know, part of the questions about solar wind, but it is always there. SEPs, and part of what distinguishes them is, first of all, is they are much higher energies. So solar wind is down at, you know, basically 1 keV protons, right? It peaks around that, and it shifts a little bit depending on the speed of the solar wind, obviously. But it's basically has a huge peak way down there, but then it drops off dramatically as you come into higher energies. I'm actually wondering whether I should bring up a plot, but I'll just try and wave my hands. And so then when you get up to higher energies, that's where you see the energetic particles, right? And so during quiet times, there's basically not much there. It's what we call the superthermals. There's like maybe a little small density of particles that are probably what we call the tail of the solar wind. But when an SEP event goes off, and SEPs are episodic, right? So they don't happen all the time. They happen, you know, you have an actual event, something happens. And it's pretty much always associated with either a flare or a CME or both. So there's something that happens on the sun and it accelerates a bunch of particles to a higher energy, usually hundreds of keV. So, you know, factors of 100 higher in energy than the solar wind is. And you see a big increase of particles at those energies. And that's what we call an SEP event. And so basically it's something that comes and goes, whereas the solar wind is always there. You can sort of always measure it. So the SEP events, they're literally events. So they start and they usually go up very fast. So they go, you know, big influx of particles, and then they kind of dribble off in terms of the intensity, and then eventually go down to background. And that's when you say like the event's over. And it's separated from the solar wind because it's at much higher energies. Does that make sense?
Yeah, like a spike, maybe we can say.
Yeah, I mean, it isn't spike in the sense that it doesn't come straight back down again, but it goes up and then it decays. Yeah, So it's sort of triangular. Now, there's lots of reasons why it won't be triangular, but we don't have to worry about that right now. So, it basically goes up really fast and then kind of comes down really slow. But there's a start and an end kind of to it, whereas the solar wind, always there.
Yeah, thank you. Thank you so much.
Yeah, sure. Yeah, no problem. Mohammed.
Excuse me, quick question. So I was wondering about the difference between the integrated energy and differential energy, because I think, as I understand, the differential energy is like the subtraction of two energy bands, or the count of particles between two energy bands, and the integrated energy is like the sum of the counts over a certain period of time. Is this correct though? Or something?
So integrated versus differential energies, you'll see this particularly the GOES spacecraft, which I didn't talk about, provides energetic particle data, and they often provide it in what they call integral channels and differential channels. So basically what you said is pretty much exactly correct. We usually do it a little bit the other way around. So differential is an intensity over a fixed energy interval. Now that interval can be wide or it can be narrow, depending on how you design your instrument and so forth and so on. But a differential energy is basically takes into account that energy then. Okay, and if you look at the units are sort of particles per solid angle, centimeter squared steradian, right, which is the size of your detector per energy. So it'll be per MeV per nucleon or per keV or something like that, right? So it takes into account the size of your energy range. An integral, and we often measure actual measurements because the way our detectors are set up, we're actually measuring particles generally in an energy band because, the particles, come in and particles of a particular energy band will stop in the same detector, right? If it gets too big, if it's too low in energy, it won't reach that detector. If it's too big in energy, it'll go down to the next detector. So often we say, okay, all the particles that stopped in this energy, in this detector are of a particular energy band. And so we can measure those. So that's often what we do is we measure differential intensities as a function, at different energy bands. Sometimes we want to talk about integral intensities, integral energy intensities, I guess is the way to say it. And so what we end up doing is we end up adding all those bands together, right? So we take the intensity, the differential intensities of that one band, we multiply it by the width of that band, and then we do the next one and we add them together and the next one and add them together. So in the end, you're sort of getting a measure of all the particles above a particular energy. So it's basically the integration of all the particles. Now, the problem is we don't measure up to infinity, right? So the integration is always somewhat limited to how high an energy you can measure. So if I build an instrument that can only measure from between 1 and 10, I can add up all those little bins and call it a greater than 1 integral intensity. But in reality, I don't know, I haven't included everything that's above 10. Now goes up to, I don't know, 500 MeV or something. And so by that time, the amount of stuff that you're adding in, because it falls off with energy, the amount of stuff you're adding in is small. So they can give you a greater than 10 MeV integral intensity, which is probably pretty accurate, right? Even though they're not measuring the stuff above 500, it's probably a small contribution. So probably what they're giving you is primarily truly an integral thing. So that's basically the difference. And there's different reasons why you would want one or the other. The differential intensities tell you more about the science about accelerating the particles and the distribution of particles in energy, and you kind of want to know that. The integral intensities are more important when you're calculating, say, radiation dose. So if you want to know how bad the impact is on the health of the spacecraft or the health of the people or, something like that, you kind of want to know all of the particles, regardless of what energy they are, above some amount, because they're all going to cause problems. And so you don't really care how they're distributed in energy. If every particle greater than 10 MeV is going to, do damage to your skin cells or something like that, or to your health, you just want to know how many there are. And so they use those kind of things to calculate what they call dose and radiation risks and things like that. So I would say that's sort of the different uses of them. they're, GOES reports the integral thing because they are often being used for calculating dose and stuff, but most of the science instruments won't report integral intensities. They'll give you the differential intensities, but you can kind of go from one to the other. It's hard to take the integral intensities and go backwards. You could kind of do what you were talking about of like take the greater than 10 integral and subtract it from the greater than 30, and that should give you a 10 to 30. But I can tell you from experience, it doesn't always work out. So like I'll get a number, but then I'll compare that to what I know is actually measured from 10 to 30, and it often doesn't match. So, but it's easy. Generally, you go the other way. You measure the actual differential intensities and you calculate the integral intensities, generally, for the instruments we have. Does that help?
Thanks so much. Thank you.
Okay, sure.
All right. Looks like you outlasted them.
I tried though. I'm now 49 messages behind in the chat, and God only knows what's happening in Slack. So,
Well,
the most
think
important thing is I need more tea. I went through all my tea.
you should go get more tea because I need you for the next couple of hours.
I know. Okay, I'm gonna go do.
Okay. And for anybody who's listening, please check Slack for the new synchronous group assignments. They are posted under the synchronous activities channel. Yeah, sync activities is the channel name. Let's see. Which I'm going to put in the general channel.
Nick, are you talking to the group? I see your mouth moving, but I don't hear what you're saying.
I am talking to myself.
Oh, okay.
I didn't realize I was on. Thank you, Shelley.
I was wondering the same thing too.
Oh, great. Okay. Please watch. Yes.